Isaac Newton. Beyond the Apple by the Sleepy Universe. Chapter 1. The Curious Boy Called Newton. On a cold winter morning in the English countryside, when the world was lit only by candlelight and the stars seemed impossibly bright, a tiny baby entered the world who was never expected to survive. His name was Isaac Newton. He was so small that people later said he could have fit inside a large drinking mug. His family feared every day might be his last. In the 17th century, babies born so early rarely lived for long. But history had other plans. No one looking at that fragile infant could have imagined that one day he would change humanity's understanding of the universe forever. Newton did not arrive in a palace or a university. He was born in the quiet village of Woolsthorpe, surrounded by fields, trees, streams, and open skies. There were no computers, no electricity, no engines, no aeroplanes crossing overhead. At night, darkness truly was dark. Yet those same stars that filled the night sky would become some of his greatest teachers. Long before Newton ever wrote a mathematical equation, he was simply a curious child. Curiosity is a strange thing. Some people see rain and think only of getting dry. Others wonder where the rain comes from. Newton belonged to the second group. He wanted to know why. Why does water fall? Why does the moon stay in the sky? Why do shadows move? Why does the wind change direction? Why do birds fly? Those questions may sound ordinary today, but during Newton's childhood there were very few reliable answers. Much of what people believed came from tradition rather than experiment. Newton would eventually change that. His father had died before he was born, leaving the family without the man who should have guided him through childhood. When Isaac was still very young, his mother remarried and moved away, leaving him to be raised by his grandparents. Many historians believe this lonely beginning shaped his personality. Instead of seeking crowds, he sought books. Instead of noisy conversation, he enjoyed quiet observation. Instead of accepting answers, he searched for better ones. His greatest companion became his own imagination. Children often take things apart to see how they work. Newton was no different. He built miniature windmills. He designed water wheels. He made sundials that could tell the time surprisingly accurately. Every object became a puzzle waiting to be solved. To most people, a clock simply tells the time. To Newton, it was a mystery of moving parts. If gears could measure hours, could nature itself also run like a giant clock? That simple thought would one day become one of the greatest scientific ideas ever conceived. The world around him wasn't random. Perhaps it followed rules. Hidden rules. Rules that anyone could discover if they looked carefully enough. As Newton grew older, school introduced him to reading, mathematics, and Latin. At first he wasn't considered an outstanding student. In fact, some classmates outperformed him. But Newton possessed something far more powerful than natural talent. Persistence. When he became interested in something, he refused to stop until he understood it completely. Hours became days. Days became weeks. Questions became discoveries. Many people work hard. Very few become obsessed. Newton did. His notebooks filled with sketches, calculations, observations, and ideas. Every blank page invited another question. Every answer created two more. This habit would stay with him for the rest of his life. Centuries later, scientists, engineers, programmers, and inventors would all share this same habit. Ask. Observe. Test. Learn. Repeat. Although Newton could never have imagined today's world of satellites, smartphones, and artificial intelligence, he helped create the way of thinking that made them possible. Every scientific breakthrough begins with curiosity. Curiosity begins with a question. One day, Newton looked up into the sky. The moon hung silently above him. People had watched the moon for thousands of years. Poets admired it. Sailors navigated by it. Lovers wrote songs about it. Newton asked a different question. Why doesn't it fall? It sounds obvious today, but no one had explained it properly. That question would eventually change astronomy forever. Before he could answer it, however, Newton had much to learn. Books became his gateway into worlds he could never visit. He devoured everything he could find about mathematics, philosophy, astronomy, mechanics, and nature. Knowledge wasn't something to collect. It was something to build upon. Imagine standing at the bottom of a mountain. Every book is another step upwards. Newton climbed relentlessly. Soon, he would leave his quiet village behind and travel to one of England's greatest universities. There, surrounded by brilliant minds and ancient libraries, his curiosity would grow into genius. But even then, he would remain the same boy who wondered why shadows moved across the ground and why stars stayed in the heavens. Great discoveries rarely begin with certainty. They begin with someone asking a question that everyone else overlooked. That was Isaac Newton's greatest gift. Not mathematics. Not physics. Not even genius. It was his refusal to stop asking why. Chapter 2: Cambridge and the Years of Plague, Part 1. The road from Woolsthorpe to Cambridge was more than a journey across the English countryside. For Isaac Newton, it was a journey into a new world. The fields and streams of his childhood were giving way to grand stone buildings, ancient libraries, and classrooms filled with young men who dreamed of changing their own futures. In 1661, at the age of 18, Newton entered Trinity College, Cambridge. The university had already stood for centuries. Its halls echoed with debates about philosophy, mathematics, astronomy, and religion. Great thinkers had walked its paths long before Newton arrived, yet many of the ideas still being taught were themselves centuries old. Students learned from the writings of the ancient Greek philosopher Aristotle. His work had shaped education across Europe for generations. But Newton was not content to accept old ideas simply because they were famous. He respected the past, yet he believed every claim should be questioned and tested. The university library became his favorite place. While others enjoyed conversation and social gatherings, Newton disappeared among rows of books. He studied mathematics late into the night, often forgetting to eat or sleep. Candles burned low as page after page filled with notes written in his neat, careful hand. He discovered the works of brilliant thinkers who had begun reshaping science. René Descartes encouraged people to reason carefully. Johannes Kepler had uncovered the mathematical patterns behind the planet's orbits. Galileo Galilei had shown that careful observation could overturn long-held beliefs. Newton admired them all. Yet as he copied equations and studied their discoveries, another thought quietly formed in his mind. What comes next? Most students aimed to learn what was already known. Newton wanted to discover what nobody knew. His notebooks became laboratories of thought. Instead of simply recording lectures, he filled margins with questions, diagrams, and ideas of his own. Mathematics fascinated him because it seemed to reveal hidden patterns beneath nature itself. Every curve, every shadow, every moving object appeared to follow rules waiting to be uncovered. Then, in 1665, everything changed. A deadly disease swept through England. The Great Plague spread rapidly from town to town. Fear traveled almost as quickly as the illness itself. Markets emptied. Streets fell silent. Families shut themselves indoors, hoping the sickness would pass them by. To protect its students, Cambridge closed its doors. Newton packed his belongings and returned to Woolsthorpe. At first, it may have felt like a disappointment. His education had been interrupted, and the future seemed uncertain. But history would remember those months very differently. Away from lectures, examinations, and daily routines, Newton found something precious. Time. Time to think. Time to observe. Time to imagine. The quiet countryside that had nurtured his curiosity as a child welcomed him once again. The same orchards, fields, and open skies now became the setting for ideas that would transform science forever. Many people see isolation as empty. Newton saw it as opportunity. Without realizing it, he was about to begin what many historians call the most astonishing period of creative thought ever achieved by a single person. The discoveries that emerged from these quiet months would eventually explain the movements of planets, the behavior of falling objects, the nature of light, and even provide the mathematical language scientists still use today. And it all began with one young man, a notebook, and an endless determination to understand how the universe truly worked. Part 2. The world outside was gripped by fear. Church bells rang more often than usual. Homes stood empty. Travelers avoided villages where illness had taken hold. Across England, life slowed to an uneasy silence as the Great Plague spread from town to town. For most people, this was a time of uncertainty. For Isaac Newton, it became a time of extraordinary thought. Back at Woolsthorpe Manor, he had no famous professors standing over him, no lectures to attend, and no examinations to prepare for. Instead, he had something far more valuable, a quiet place where his mind could wander as freely as the clouds drifting across the Lincolnshire sky. Each morning, Newton would wake with questions already forming in his thoughts. He observed everything around him with remarkable care. The movement of birds across the fields, the changing position of the sun, the rhythm of flowing water. Even the smallest details seemed to hint at invisible rules governing the natural world. To many people, nature appeared messy and unpredictable. To Newton, it resembled a giant puzzle. He believed every piece fitted somewhere. The challenge was discovering where. His notebooks multiplied. Every page became crowded with calculations, sketches, and ideas. Sometimes he wrote so quickly that only he could understand his own handwriting. When one question led to another, he simply turned the page and kept going. There were no computers to perform calculations. No electronic calculators. Not even mechanical machines capable of solving difficult mathematics. Everything happened inside Newton's own mind. Yet that mind seemed capable of exploring places no one else had reached. One problem fascinated him more than most. How could mathematics describe things that were constantly changing? Imagine watching a horse gallop across a field. Its position changes every moment. Its speed changes. Its direction changes. How could numbers keep up with something that never stayed still? The mathematics of the day worked well for measuring objects that remained fixed. But moving objects were different. Newton wanted a new language. A language that could describe motion itself. Slowly, almost secretly, he began developing ideas that would later become known as calculus. At the time, he didn't give it a grand name. To him, it was simply another tool for understanding nature. He imagined quantities that flowed like water rather than remaining fixed like stones. Instead of asking where something was, he asked how quickly it was changing. That simple shift in thinking opened an entirely new branch of mathematics. Today, calculus helps engineers design bridges, predicts the paths of spacecraft, allows doctors to model the human heart, and enables computers to simulate weather, oceans, and even galaxies. Yet its beginnings were surprisingly humble. One young man. One country house. One restless imagination. As his mathematical ideas grew stronger, Newton noticed something remarkable. The same equation seemed useful in many different situations. The path of a falling object. The curve of a planet's orbit. The swing of a pendulum. The flow of water. Different problems. Yet somehow connected. Nature wasn't made from separate mysteries. It was one great mystery with many faces. That thought thrilled him. It suggested that the universe itself might operate according to elegant mathematical laws. If those laws could be discovered, then perhaps almost everything, from the flight of an arrow to the movement of the moon, could be explained. This was a revolutionary idea. For thousands of years, people often described nature through stories or philosophy. Newton wanted something stronger. Proof. Evidence. Equations that anyone could test. He wasn't interested in winning arguments. He wanted to uncover truth. As autumn turned to winter, his work continued. The orchard outside his window changed with the seasons. Leaves drifted gently to the ground. Frost covered the grass in the early mornings. The night sky sparkled with countless stars, each one silently following its path across the heavens. Newton often looked upward. The stars seemed peaceful, but his mind was racing. He couldn't shake one enormous question. If objects fall to Earth, why doesn't the moon? That single question refused to leave him. He sensed the answer was close, hidden just beyond his current understanding. He had the mathematics. He had the curiosity. Now he needed one final insight that would connect the earth beneath his feet with the heavens above his head. That insight, inspired by one of the most famous stories in the history of science, would soon change humanity's understanding of the universe forever. Part 3. The story has been told for centuries. Almost everyone has heard it. A young Isaac Newton sits quietly beneath an apple tree. Suddenly, an apple falls from a branch and lands on the ground. In that instant, he discovers gravity. It is a wonderful story. But like many famous stories, the truth is a little more interesting. There is good evidence that Newton really did see an apple fall while at Woolsthorpe. Years later, he told friends about watching apples drop from trees and wondering why they always fell straight toward the earth. The apple probably did not strike him on the head. That part was added much later, but the falling apple did inspire a remarkable question. Why down? Why not sideways? Why not upwards? What was pulling the apple towards the ground? Most people would have picked up the apple and carried on with their day. Newton could not let the question go. As he looked at the apple lying in the grass, his thoughts leapt far beyond the orchard. If the earth can pull an apple, he wondered, could it also pull the moon? At first, that sounds impossible. The moon is almost 400,000 kilometers away. It circles the earth every month without crashing into it. Surely the force that pulls an apple to the ground couldn't reach that far. Or could it? Newton imagined throwing a stone. Throw it gently, and it falls nearby. Throw it harder, and it travels farther. Now imagine throwing it so fast that, as it falls, the earth curves away beneath it. It would keep falling forever without ever hitting the ground. Today we call that an orbit. This simple thought experiment helped Newton picture something extraordinary. The moon wasn't floating because there was no gravity. It was falling. Constantly. But it was moving sideways so quickly that it kept missing the earth. This was a completely new way of looking at the heavens. Before Newton, many people thought the skies and the earth obeyed different rules. The planets belonged to one world. Falling apples belonged to another. Newton dared to suggest they were governed by the very same law. The force pulling the apple downward was the same force keeping the moon in its endless journey around our planet. One rule. Two very different worlds. The idea was breathtaking. If it was true, then perhaps every object in the universe attracted every other object. The sun held the planets. The planets held their moons. Even you and the chair you're sitting on attract each other, although the force is so tiny you never notice it. Nature suddenly became beautifully connected. The universe was not a collection of separate events. It was one immense system, woven together by invisible threads. Of course, ideas alone were not enough. Newton knew that. Anyone can have an idea. A scientist must prove it. So he turned once again to mathematics. Hour after hour, he calculated. He compared the distance to the moon with the strength of gravity on Earth. He measured, estimated, corrected mistakes, and started again. Sometimes the numbers refused to agree. Rather than forcing an answer, Newton questioned his own work. If nature disagrees with me, he thought, then I must have more to learn. That willingness to admit mistakes became one of his greatest strengths. Science is not about proving yourself right. It is about discovering what is true. Eventually, the calculations began to fit together. The same mathematical ideas that described a falling apple also described the path of the moon. It was one of the greatest moments in the history of human thought. Without leaving his quiet home in Woolsthorpe, Newton had begun uncovering the invisible architecture of the cosmos. He could not yet know where these discoveries would lead. Centuries later, scientists would use the same principles to launch satellites into orbit, send astronauts to the moon, guide robotic explorers across Mars, and steer spacecraft beyond the edge of our solar system. Every one of those journeys would begin with equations that first took shape in the mind of a young man sitting in the English countryside during a time of plague. But Newton was not finished. Far from it. As remarkable as gravity was, another mystery continued to capture his imagination. Whenever sunlight streamed through his bedroom window, he noticed something curious. The light seemed pure, simple, white. Yet he suspected it was hiding a secret. A secret that would change the way humanity understood color itself. Morning sunlight poured through the small windows of Woolsthorpe Manor, filling the room with a warm golden glow. To most people, sunlight was simply light. It brightened the day, warmed the skin, and helped crops grow. Newton saw something different. He saw another mystery. What exactly was light? For centuries, people believed white light was pure and simple. If colors appeared in a rainbow, many assumed the raindrops somehow created them. Newton wasn't satisfied with assumptions. He wanted evidence. One day, he darkened a room by closing the shutters, leaving only a tiny hole through which a narrow beam of sunlight could enter. Into that beam he placed a glass prism. What happened next amazed him. The white beam spread out into a brilliant band of colors across the wall. Red, orange, yellow, green, blue, indigo, violet. A rainbow indoors. It was a beautiful sight, but Newton wasn't interested in beauty alone. He wanted to know why it happened. Many people thought the prism had somehow colored the light. Newton suspected something very different. He took a second prism and carefully passed just one color through it. The color remained the same. Then he used another prism to bring all the colors back together again. The result? White light returned. It was an astonishing discovery. The prism had not created the colors. They had been hiding inside the white light all along. White light, Newton realized, was not simple at all. It was a mixture of many colors, each bending by a slightly different amount as it passed through the glass. Today, every school student learns this idea, but in Newton's time it completely changed the science of optics. Without knowing it, he had opened the door to technologies that would appear centuries later. Modern cameras, microscopes, telescopes, laser surgery, fiber optic internet cables carrying billions of messages around the world at the speed of light. Even the way scientists study distant galaxies depends on understanding how light separates into different colors. Newton could never have imagined people making video calls across continents or using tiny glass fibers to stream films into their homes. Yet his experiments with a simple prism helped make those inventions possible. As the months passed, the plague slowly faded, and Cambridge prepared to welcome students once more. Newton packed away his notebooks. Inside them were ideas unlike anything the world had seen. New mathematics. New ways of thinking about motion. The first foundations of universal gravitation. Remarkable discoveries about light and color. He had made these breakthroughs before the age of 25. Few people realized what had happened during those quiet months in Woolsthorpe. There had been no cheering crowds. No newspaper headlines. No awards. Just one young scholar filling notebook after notebook with ideas that would one day reshape civilization. History would later call these his years of wonders. It is difficult to find another period in which a single person contributed so much to human knowledge in such a short time. Yet Newton himself remained humble. Years later, he wrote one of the most famous reflections in scientific history. If I have seen further, it is by standing on the shoulders of giants. He understood that every discovery builds upon those that came before it. Knowledge is like a great bridge. Each generation lays new stones so the next can travel farther. Newton's stones would become some of the strongest ever placed. When he returned to Cambridge, he was no longer simply a talented student. He carried with him ideas that would transform mathematics, physics, astronomy, and the scientific method itself. The world did not know it yet, but it was about to meet one of the greatest scientific minds in history. And Newton's greatest works were still to come.
Chapter 3: The Birth of Calculus.
Part 1. Imagine trying to describe a single photograph. Now imagine trying to describe an entire movie. A photograph captures one frozen instant in time. A movie is different. Every second, the picture changes. People move, objects accelerate, shadows shift, and events unfold continuously. The mathematics of Newton's day was excellent at describing the photograph. Newton wanted mathematics that could describe the movie. Without realizing it, he was about to create one of the most powerful tools ever invented by the human mind. When Isaac Newton returned to Trinity College, Cambridge, he carried more than notebooks filled with ideas. He carried questions that no one else had yet answered. He had begun to understand that nature was constantly changing. A leaf drifting from a tree speeds up as it falls. A horse galloping across a field is never in exactly the same place twice. The moon circles the earth without ever stopping. The tides rise and fall. Clouds gather and disappear. Even time itself seems to flow like a river. If everything in nature is always changing, how can mathematics keep pace? That question became Newton's obsession. At the time, mathematicians could measure lengths, areas, and volumes with remarkable accuracy. They could calculate the size of buildings or the distance between towns. But describing something that was changing every instant was far more difficult. Newton believed there had to be a better way. He imagined quantities not as fixed numbers, but as things that flowed. He thought of them almost like water moving along a river. Some flowed quickly, others slowly. Some sped up, while others slowed down. He called these changing quantities fluents. The speed at which they changed became their refluxions. Today, mathematicians use different names. We call this branch of mathematics calculus. The names have changed. The ideas remain. To understand why calculus is so important, imagine driving a car. Your speedometer tells you how fast you're traveling right now. Not your average speed over an hour. Not how fast you were 5 minutes ago. This exact moment. That simple idea lies at the heart of calculus. Newton wanted mathematics that could answer questions like, how fast is something moving at this instant? How quickly is its speed changing? Where will it be in 10 seconds? How will its path change if another force acts upon it? These questions sound ordinary today because calculus has become part of science and engineering. In Newton's time, they were revolutionary. As he worked through page after page of calculations, he noticed something beautiful. Many different problems shared the same mathematical patterns. The path of a cannonball, the swing of a pendulum, the orbit of a planet, the growth of a plant. They looked different on the surface. Deep down, they followed similar rules. Nature, Newton realized, was speaking one mathematical language. Humanity simply hadn't learned to read it yet. His work demanded incredible concentration. Friends later recalled that Newton often became so absorbed in his thinking that he forgot to eat. Meals grew cold while he filled another page with symbols and diagrams. Sometimes he stood silently for long periods, staring out of a window. To anyone passing by, he appeared lost in thought. In reality, entire universes were unfolding inside his mind. He was not merely solving equations. He was inventing new ones. He wasn't simply learning mathematics. He was expanding it. Every discovery seemed to reveal another layer beneath it. The deeper he looked, the more connected everything became. Mathematics wasn't separate from nature. It was nature's hidden grammar. And Newton was slowly learning to read it. Yet he was also remarkably cautious. Unlike many scholars eager to publish every new idea, Newton often kept his discoveries private. He feared criticism and wanted to be certain his work was correct before sharing it with the world. That caution meant many of his greatest ideas remained hidden in notebooks for years. It also meant that, elsewhere in Europe, another brilliant mathematician was exploring similar ideas. Before long, the question would arise: who invented calculus first? The answer would become one of the greatest disputes in the history of science. But beyond the arguments over credit lay something far more important: calculus itself. It became the mathematical engine behind the modern world. Every rocket launched into space, every bridge spanning a river, every aircraft crossing an ocean, every weather forecast, every GPS route, every MRI scanner in a hospital, every computer simulation predicting the spread of a wildfire or the path of a hurricane. Even many of the algorithms used in today's artificial intelligence systems rely on ideas that trace their roots back to calculus. Newton could never have imagined self-driving cars, reusable rockets, or robots exploring Mars. Yet the mathematical language he created helps make all of them possible. As he sat at his desk in Cambridge, surrounded by candles, parchment, and ink, he was doing far more than solving difficult problems. He was giving future generations a tool powerful enough to explore worlds he would never live to see. And this was only the beginning.
Part 2.
Great discoveries often raise an unexpected question. Not is it true, but who thought of it first? As Isaac Newton quietly refined his new mathematics in England, another brilliant thinker was asking remarkably similar questions hundreds of miles away in Europe. His name was Gottfried Wilhelm Leibniz. Like Newton, Leibniz was fascinated by patterns, logic, and the hidden language of mathematics. He believed that complex ideas could be broken into simpler parts and understood through careful reasoning. Although the two men had never worked together, they were traveling along surprisingly similar paths. It was as if two explorers had set out from opposite sides of a vast mountain range, each searching for the same hidden valley. Neither knew the other was coming. Both eventually arrived. Newton had developed his methods during the plague years of the 1660s but kept most of his work private. He preferred to revise, improve, and question every detail before revealing it to the world. Leibniz, on the other hand, published his ideas more openly. As mathematicians across Europe began reading Leibniz's work, many naturally assumed that he had invented this remarkable new branch of mathematics. When Newton's supporters realized this, a fierce argument erupted. Letters were exchanged. Accusations were made. Friends took sides. The scientific world became divided. Did Newton invent calculus first? Or had Leibniz reached the idea independently? Today, historians generally agree that both men developed calculus independently, each using different approaches and different notation. Newton's ideas came earlier, but Leibniz published first and created much of the notation that mathematicians still use today. In a way, both left an enduring legacy. Newton gave the world profound physical insight. Leibniz gave the world elegant mathematical symbols. Together, their work transformed science forever. Newton himself was deeply upset by the dispute. Normally quiet and private, he became defensive when he believed his life's work was being questioned. The disagreement lasted for years and cast a shadow over what should have been a celebration of one of humanity's greatest intellectual achievements. Yet history eventually looked beyond the argument. What mattered most was not who held the pen first. What mattered was the extraordinary power of the ideas. Imagine trying to design a roller coaster. Every hill, every curve, every drop must be calculated precisely. Too steep, and it becomes dangerous. Too shallow, and it loses its excitement. Calculus allows engineers to predict exactly how the coaster will move. Now imagine replacing the roller coaster with a spacecraft heading for Mars. The challenge is larger. The mathematics is the same. Or imagine a doctor studying how medicine travels through the bloodstream. Or an architect designing a skyscraper that must withstand strong winds. Or a climate scientist predicting the path of a hurricane. Different fields. One mathematical language. This is why many historians describe calculus as one of the greatest inventions in human history. It doesn't simply solve one problem. It helped solve thousands. Newton could never have imagined a world where computers perform billions of calculations every second. But every time those computers predict the weather, animate a film, train an artificial intelligence, or calculate the safest route for an aircraft, they rely on mathematical ideas built upon the foundations he helped create. It is astonishing to think that equations first written with ink on rough paper now guide satellites orbiting high above the Earth. The language of change had become the language of the modern world. But Newton was already thinking beyond mathematics. To him, equations were never the final goal. They were tools. The real prize was understanding nature itself. What force made an object speed up? Why did some things keep moving while others slowed down? Could every movement, from a rolling cart to a planet circling the sun, be explained by a small number of simple rules? These questions drew Newton toward what would become his greatest masterpiece. A set of principles so elegant that they would shape science for more than 3 centuries. Soon, the world would learn about the laws of motion, 3 deceptively simple ideas that explained everything from a child's toy cart to the flight of rockets into deep space. Those laws would not only change science, they would change civilization itself.
Part 3.
Isaac Newton often reminded himself of a simple truth. Nature does not change its rules simply because the objects become larger or smaller. That idea may seem obvious today, but in the 17th century it was revolutionary. Many people believed the heavens and the earth obeyed different laws. The stars belonged to one realm, while everyday life belonged to another. Newton believed there was only one universe. If the same mathematics could describe a falling apple and the orbit of the moon, then perhaps all motion followed a small set of universal principles. His new mathematics, calculus, gave him a powerful language. But a language is useful only if it has something important to say. Newton now turned his attention to one of the oldest questions in science. Why do things move the way they do? For centuries, philosophers had debated this question. Some believed that an object needed a constant push to keep moving. If a cart rolled across a road and eventually stopped, it seemed obvious that motion naturally faded away. Newton looked more carefully. He realized the cart stopped because of friction, the resistance between the wheels and the ground, and the air pushing against it. Imagine, he thought, a world with no friction at all. What would happen? A ball rolled across such a surface would never slow down. It would keep moving forever. This was a startling conclusion. Motion was not something that needed to be continually created. Instead, motion continued naturally unless something interfered. It was a simple idea with enormous consequences. Today, we see it every time a spacecraft glides silently through the vacuum of space. With almost no friction to slow it down, it can travel for years using only occasional bursts from its engines. Newton could never have seen a spacecraft. Yet his reasoning described one perfectly. This ability to imagine impossible situations became one of his greatest strengths. He performed experiments whenever he could, but many of his greatest experiments took place in his imagination. What if there were no air? What if there were no friction? What if gravity reached all the way to the moon? These thought experiments allowed him to explore ideas that could not yet be tested directly. Centuries later, scientists such as Albert Einstein would use the same approach, imagining journeys on beams of light or elevators floating through space. Imagination, Newton showed, was not the opposite of science. It was one of its greatest tools. As his calculations became more refined, Newton noticed that force, mass, and motion were deeply connected. A light object was easier to accelerate than a heavy one. A gentle push produced only a small change. A stronger push produced a greater change. There was order behind every movement. Nothing happened by chance. Every effect had a cause. Every change followed a rule. His notebooks became filled with diagrams of moving objects, arrows representing forces, and equations linking them together. To an outsider, they may have looked confusing. To Newton, they were revealing the hidden machinery of the universe. It was as though nature had always been speaking quietly, waiting for someone patient enough to listen. And Newton was listening. He did not yet know that these ideas would eventually be gathered into one extraordinary book, Philosophiae Naturalis Principia Mathematica, usually known simply as the Principia. Published years later, it would become one of the most influential scientific books ever written. Inside its pages, Newton would present the 3 laws of motion, showing that the same principles govern a rolling marble, a sailing ship, a cannonball, the moon, and the planets themselves. The ideas were elegant because they were simple. The consequences were astonishing because they were universal. Today, engineers still use these principles to design cars with safer brakes, aircraft that fly efficiently, bridges that withstand heavy loads, and rockets that escape Earth's gravity. Even robots exploring Mars rely on calculations based on Newton's laws. The mathematics has grown more advanced over the centuries, but its foundation remains remarkably familiar. Newton had begun by asking how things change. Now he was discovering why they change. The answers would soon reshape humanity's understanding of motion forever. And with those answers, Isaac Newton would take another step toward becoming one of the greatest scientists the world has ever known.
Part 4.
By the middle of the 1660s, Isaac Newton had become increasingly frustrated by the limits of existing mathematics. Geometry could describe shapes with remarkable precision, but it struggled to explain continuous change. Nature, however, never stood still. A planet never paused in its orbit. A falling apple never descended in separate steps. A wave upon a pond never jumped from one position to another. Everything flowed. Newton believed mathematics should flow as well. Most mathematicians worked with fixed quantities, numbers that could be measured and compared. Newton began imagining quantities that were always changing. Rather than asking where an object was, he wanted to know how quickly its position changed from one instant to the next. That simple question would become one of the greatest revolutions in human thought. Working alone in Woolsthorpe during the plague years, Newton filled notebook after notebook with calculations unlike anything seen before. He called changing quantities fluents. Their rates of change he named fluxions. Today those ideas are known by different names. We call them functions and derivatives. Although the terminology changed, the heart of Newton's idea remains exactly the same. Imagine watching rain fill a bucket. At first only a few drops fall. Then the rain becomes heavier. Finally the storm eases. The amount of water inside the bucket is always increasing, but the speed of that increase changes constantly. Newton realized mathematics needed a language capable of describing that changing speed at every instant. Not every minute. Not every second. Every single moment. One evening he drew a curve across a page. Rather than measuring the curve itself, he imagined placing a tiny point upon it. If the point moved just an unimaginably small distance, how steep would the curve be right there? Not nearby. Exactly there. This was an impossible question using ordinary geometry. Yet Newton believed the answer existed. He imagined intervals becoming infinitely small, not quite zero, but smaller than any measurable quantity. From these vanishing quantities emerged an entirely new way of thinking. Instead of studying objects, mathematics could study motion. Instead of describing results, it could describe processes. Nature itself suddenly became calculable. Newton often worked through the night. Candles burned down to puddles of wax. The ink on his fingers never completely disappeared. Food frequently went untouched until morning because he had forgotten to eat. Visitors later described him as absent-minded, but in truth his concentration bordered on obsession. He once became so absorbed in a calculation that he failed to notice an entire meal had been placed beside him. Hours later the food remained untouched. The mathematics had consumed him. His notebooks reveal page after page of experimentation. Many calculations ended in failure. Entire sheets were crossed through. Mistakes filled the margins. Yet each error carried him closer to something extraordinary. Newton rarely viewed failure as defeat. To him it was merely another clue. Each incorrect answer narrowed the path toward the correct one. The breakthrough arrived quietly. There was no audience, no applause, no dramatic announcement. One calculation simply worked. Then another. Soon an astonishing pattern emerged. The mathematics governing change also explained the areas enclosed by curves. Problems that had once seemed completely unrelated were actually two sides of the same coin. Finding a slope, finding an area, differentiation, integration. Newton had unknowingly discovered what is now called the fundamental theorem of calculus. It remains one of the most elegant relationships in all mathematics. To appreciate its significance, imagine driving along a motorway. Your speedometer tells you your speed at every instant. That is the rate of change. Now imagine recording that speed every second throughout your journey. From those changing speeds alone, you could calculate the total distance traveled. One process describes instantaneous change. The other adds those tiny changes together. Newton proved these ideas were inseparable. The discovery transformed mathematics from a collection of techniques into a complete language for describing motion. His new method solved problems that had puzzled mathematicians for generations. The paths of projectiles, the motion of planets, the bending of light, the flow of rivers, the growth of populations. Although Newton himself could not foresee every application, the possibilities seemed endless. Nature had always obeyed mathematical laws. Humanity had finally begun learning the language. Remarkably, Newton showed little interest in publishing these discoveries. He feared criticism. He disliked arguments. More importantly, he believed incomplete work should remain private. Many of his greatest ideas sat hidden inside handwritten manuscripts for years. Had history taken a slightly different course, they might never have become known. Across Europe, another brilliant mathematician was approaching similar ideas. His name was Gottfried Wilhelm Leibniz. Working independently, he developed his own version of calculus using a notation that mathematicians still employ today. Neither man initially knew how closely their work overlapped. What began as two separate discoveries would later ignite one of history's bitterest scientific disputes. For now, however, Newton remained unaware. His concern was not fame. His concern was understanding. As winter settled over Woolsthorpe, Newton closed another notebook. Around him the countryside appeared unchanged. Fields slept beneath frost. The stars crossed the sky as they always had. Neighbors saw only a quiet young scholar returning from Cambridge. None suspected that inside those notebooks rested an invention as powerful as algebra itself. Calculus would eventually become the foundation of engineering, astronomy, economics, medicine, computer graphics, artificial intelligence, and space exploration. Every modern spacecraft navigating between planets relies upon mathematics descended directly from these lonely evenings. Every bridge designed by engineers. Every aircraft in flight. Every weather forecast. Every satellite orbiting Earth. All trace part of their mathematical ancestry to the work Newton quietly completed before reaching his 24th birthday. History often remembers great discoveries as moments of sudden inspiration. The truth is usually far quieter. A solitary room. A determined mind. Thousands of failed calculations. And one person refusing to stop asking how the universe really works. Newton had not merely solved a mathematical problem. He had given humanity a new way to understand change itself. The next challenge would be even greater. Armed with his new mathematics, he would begin asking why the moon never fell to Earth, and why the planets continued their endless journeys around the sun. Those questions would lead directly to one of the greatest scientific discoveries ever made.
Part 5.
The first ideas of universal gravity. The young Isaac Newton had already changed mathematics forever. But mathematics was only the beginning. During his years at Woolsthorpe, while the world outside struggled through the uncertainty of the plague, Newton began turning his attention toward a question that had fascinated humans for thousands of years. Why do things fall? Everyone knew that objects dropped toward the ground. A stone released from a tower descended. Rain fell from clouds. An apple separated from its branch and landed beneath the tree. But knowing that something happened was very different from understanding why. For centuries, philosophers had accepted the ideas of ancient thinkers who believed that earthly motion and the movement of the heavens belonged to completely different worlds. The earth was imperfect and changing. The heavens were perfect and eternal. Newton began to suspect they were connected. Looking up at the moon, Newton asked a revolutionary question. Was the moon actually falling? At first this seemed impossible. The moon did not crash into Earth. It traveled calmly across the night sky, following a predictable path. Yet Newton imagined something different. Perhaps the moon was constantly falling toward Earth but moving sideways so quickly that it continually missed. Like throwing a ball. A gentle throw sends the ball forward before gravity pulls it down. A stronger throw sends it farther. If an object could be thrown fast enough, the curve of the Earth would fall away beneath it at the same rate gravity pulled it downward. The object would never land. It would orbit. Newton realized the moon might be doing exactly this. This idea required something extraordinary. The same force that pulled an apple downward might also reach thousands of miles into space and guide the moon around Earth. Earth and sky were not separate. They were governed by the same rule. It was one of the most powerful ideas ever imagined. A single law could explain both a falling stone and the movement of planets. To test his idea, Newton needed mathematics. This was where his discovery of calculus became essential. He calculated how far an object should fall near Earth's surface. Then he compared this with how much the moon's path curved away from a straight line. His first attempt produced difficulties. The measurements available at the time were not accurate enough. The size of Earth itself was uncertain. Newton placed his calculations aside. But he did not abandon the idea. Some discoveries require waiting for the world to catch up. Years later, improved measurements gave Newton the information he needed. A more accurate estimate of Earth's size allowed him to return to his calculations. This time the numbers matched. The force pulling an apple downward and the force holding the moon in orbit appeared to be one and the same. Gravity was not simply an earthly phenomenon. It was universal. Newton began imagining a universe connected by invisible threads. Every object with mass affected every other object. The Earth pulled on the moon. The moon pulled on Earth. The sun held the planets in their paths. The planets themselves influenced each other. The universe was not a collection of separate objects moving randomly. It was an enormous system of relationships. This was a profound change in human thinking. Before Newton, many people believed the heavens operated according to mysterious principles beyond human understanding. Newton showed that the same mathematics used to study objects on Earth could explain the movements of distant worlds. The stars were no longer beyond investigation. The universe had become a place where questions could be answered through observation and calculation. Yet Newton still faced a difficult challenge. Knowing that gravity existed was not enough. He needed to describe exactly how it worked. How strong was gravity? How did it change with distance? Why did planets follow curved paths rather than flying away into space? These questions required a complete mathematical description. Newton would spend years refining his ideas. The result would become one of the greatest scientific books ever written. A work that would change humanity's understanding of nature. The journey toward that book began with a simple thought. The apple falling from the tree and the moon moving through the heavens were not two separate events. They were chapters of the same story. A story written in the language of mathematics. Newton was about to reveal the hidden structure behind the universe itself.
The road to Principia.
Building the mathematical universe. Newton had reached a remarkable conclusion. The force that pulled an apple toward the ground could also guide the moon through the heavens. But an idea, no matter how brilliant, was not enough. Science demanded proof. Newton now faced his greatest challenge, transforming a powerful insight into a complete mathematical description of the universe. The problem was enormous. The planets did not move in simple circles. Their paths were complicated. They sped up at certain points and slowed down at others. They moved around the sun while being influenced by forces that could not be seen. Ancient astronomers had created complicated systems of circles within circles to explain these movements, but Newton believed there had to be a deeper simplicity hidden beneath the complexity. Nature, he suspected, followed elegant rules. Using his newly created mathematics, Newton began exploring the relationship between force and motion. He imagined a world where objects continued moving forever unless something acted upon them. This was a radical change. Many people before him believed that constant force was needed to maintain movement. Newton saw the opposite. A moving object naturally continued moving. It was changes in motion that required explanation. From this thinking came his first great principle. An object at rest remained at rest. An object in motion continued in a straight line at the same speed unless acted upon by an outside force. This became known as the law of inertia. It explained why passengers move forward when a carriage suddenly stops. It explained why objects on Earth do not need a constant push to keep moving. It explained why planets could continue traveling through space. Newton then considered the relationship between force and acceleration. A stronger push created a greater change in motion. A heavier object required more force to achieve the same acceleration. This relationship became one of the most famous equations in history. Force equals mass times acceleration. Or simply, F equals ma. With three symbols, Newton created a mathematical bridge between the physical world and human understanding. But the greatest mystery remained. Why did gravity weaken with distance? Newton discovered that gravity followed a precise pattern. The further apart two objects were, the weaker their attraction became. The relationship followed the inverse square law. Double the distance, and the gravitational force became 4 times weaker. Triple the distance, and it became 9 times weaker. This simple mathematical relationship explained the movements of planets with astonishing accuracy. Newton began bringing together everything he had discovered. Mathematics, motion, gravity, astronomy. They were no longer separate subjects. They became parts of one complete vision. The universe was not controlled by different rules in different places. The same laws operated everywhere. On Earth, on the Moon, across the solar system, perhaps even throughout the entire cosmos. By the 1680s, Newton's ideas attracted the attention of other scientists. One of them was the astronomer Edmund Halley. Halley visited Newton and asked a question about planetary motion. If gravity followed Newton's principles, what shape would a planet's orbit take? Newton answered immediately. An ellipse. Halley was amazed. He asked Newton how he knew. Newton replied that he had already calculated it years earlier. But when Halley requested to see the work, Newton discovered that his old calculations were incomplete. The conversation inspired him to return to his research. What followed was a period of intense work. Newton began writing what would become his greatest achievement. Philosophiae Naturalis Principia Mathematica. Usually shortened to Principia. It would become one of the most influential scientific books ever created. 2. Inside its pages, Newton would present his laws of motion and his theory of universal gravitation, creating a framework that would dominate physics for more than 2 centuries. 2. The task was exhausting. Newton worked with extraordinary intensity. He refined equations repeatedly. He checked every assumption. He searched for errors before anyone else could find them. The book was not simply a collection of discoveries. It was an attempt to reveal the hidden machinery of reality. When Principia finally appeared in 1687, the world changed. Humanity now possessed a mathematical description of the universe. The skies were no longer mysterious. The movement of planets could be predicted. The behavior of objects could be calculated. The same laws that explained a falling stone explained the orbit of distant worlds. Newton had achieved something unprecedented. He had taken the chaos of nature and discovered order. Yet this triumph would bring new challenges. Recognition would come. Arguments would follow. And Newton, a man who preferred solitude and quiet study, would soon find himself at the center of the scientific world. The next chapter of his life would not only be about discovery. It would be about fame, rivalry, and the struggle to protect his legacy.
Chapter 4: The Master of Gravity, Principia and Newton's Rise to Fame.
Part 1: The Book That Explained the Universe. In the quiet halls of Cambridge, Isaac Newton began writing a book that would transform humanity's understanding of reality. It was not simply a scientific paper. It was an attempt to describe the hidden machinery of the universe. For centuries, humans had watched the skies with wonder. They tracked the movements of planets, predicted eclipses, and created calendars based on the stars. But nobody had discovered the underlying rules that controlled the heavens. Newton intended to change that. His book would be called Philosophiae Naturalis Principia Mathematica, the mathematical principles of natural philosophy. It would become known simply as Principia. The journey toward Principia had not been easy. Newton was not a man who rushed his ideas into the world. He questioned everything. Before writing a single page, he tested his theories again and again. A mistake in mathematics could lead to a false understanding of nature itself. Newton believed that if he was going to claim that the universe followed certain laws, those laws had to withstand the strongest possible examination. The central idea of Principia was revolutionary. The universe was governed by mathematical laws. Not mysterious forces. Not supernatural explanations. Not separate rules for Earth and the heavens. One system connected everything. A falling apple. A cannonball traveling through the air. The moon orbiting Earth. The planets circling the sun. All followed the same principles. Newton organized his ideas around 3 laws of motion. The first explained inertia. Objects naturally resisted changes in their motion. A stationary object stayed still. A moving object continued moving unless another force interfered. This explained why motion itself did not require a constant cause. The second law explained how forces changed motion. Newton showed that acceleration depended upon 2 things: the amount of force applied, and the mass of the object being moved. This relationship became one of the most famous ideas in physics. Force equals mass multiplied by acceleration. With this principle, Newton created a mathematical language for movement. Scientists could now calculate how objects would behave before the events even happened. The third law revealed a hidden balance in nature. For every action, there is an equal and opposite reaction. A person pushing against the ground moves forward because the ground pushes back. A rocket rises because gases are forced downward. A swimmer moves through water by pushing water behind them. Newton had discovered that forces always came in connected pairs. But the greatest achievement of Principia was not the laws of motion alone. It was the explanation of gravity. Newton proposed that every object in the universe attracted every other object. The strength of this attraction depended on 2 things: the amount of matter involved, and the distance separating them. The sun held the planets. The Earth held the moon. The moon influenced the tides. Everything was connected through gravity. When Principia was published in 1687, it changed science forever. The work presented Newton's laws of motion and universal gravitation, creating the foundation of classical physics. 2. The response from the scientific community was enormous. Some immediately recognized the importance of Newton's work. Others struggled to accept such a dramatic change in the understanding of nature. One person who played a crucial role in bringing Principia to the world was Edmund Halley. Halley had encouraged Newton to complete the work and helped arrange its publication. Without his support, the book might have remained unfinished among Newton's private papers. History sometimes depends not only on the genius of an individual, but also on those who recognize that genius. Newton had achieved what few people in history ever accomplish. He had created a theory that explained the universe on both the largest and smallest scales available to science at the time. The heavens had been brought down to Earth. The Earth had been connected to the heavens. Humanity now possessed a new vision of reality. But success would bring unexpected difficulties. Newton's discovery would make him famous. It would also place him at the center of arguments, rivalries, and conflicts that would test his character. The man who revealed the order of the universe was about to enter a world filled with human disorder.
Part 2. The Battle for Recognition, Newton and the Calculus Controversy.
Isaac Newton had achieved something extraordinary. He had revealed the hidden mathematics behind motion and gravity. But another discovery was waiting to create a storm. A discovery that would not be about planets or falling objects. It would be about pride, reputation, and the question of who had discovered one of the most important mathematical tools in history. Calculus. Years before Principia was published, Newton had developed his own method for understanding change. He had created his system of fluxions and fluents while working during the plague years. The ideas were powerful, but Newton kept them mostly private. He wrote about them in notebooks. He shared them with only a few trusted colleagues. To Newton, an unfinished idea was dangerous. He feared criticism and believed that his work should be perfect before being exposed to the world. Meanwhile, thousands of miles away in Europe, another brilliant thinker was following a similar path. His name was Gottfried Wilhelm Leibniz. Leibniz was a philosopher, mathematician, inventor, and scholar. Unlike Newton, he was much more comfortable publishing his ideas. In the late 1670s, Leibniz developed his own version of calculus. His symbols were different. His methods were different. But the underlying concept was remarkably similar. He had discovered a mathematical language for describing continuous change. At first, there was no conflict. Newton and Leibniz respected each other's intelligence. Newton even acknowledged Leibniz's abilities. But slowly, questions began to appear. Who had discovered calculus first? Had Leibniz created the idea independently? Or had he learned about Newton's earlier unpublished work? The dispute grew more intense after mathematicians in England began defending Newton. They argued that Newton had discovered calculus years earlier. They pointed to his private manuscripts and letters as evidence. Leibniz's supporters responded that unpublished ideas could not establish priority. A discovery hidden away could not influence the world. The disagreement became a scientific battle. What began as a question of mathematics became a question of honor. Newton, normally quiet and private, became deeply involved. He used his influence within the Royal Society to investigate the dispute. The resulting report supported Newton's claim. However, critics later argued that the investigation was not completely impartial because Newton himself had significant influence over the process. Modern historians generally recognize that Newton and Leibniz developed calculus independently. Newton arrived at his ideas earlier. Leibniz developed clear notation that became the foundation of modern calculus. Both men made enormous contributions. The mathematics used today owes something to both discoveries. The controversy revealed something important about Newton. Behind the image of the calm genius was a fiercely competitive person. He wanted truth, but he also wanted recognition. He had spent decades working in isolation, and he believed his achievements deserved to be protected. Yet while arguments surrounded calculus, Newton's reputation continued to grow. Principia had transformed science. Universities across Europe studied his theories. Astronomers used his mathematics to understand planetary movements. Philosophers began reconsidering humanity's place in the universe. Newton was no longer simply a Cambridge scholar. He had become one of the most famous thinkers on Earth. But fame brought responsibilities Newton had never expected. In 1689, Newton entered public life when he became a member of Parliament representing Cambridge University. He attended debates in London, but politics did not capture his imagination. According to stories from the time, Newton rarely spoke during parliamentary sessions. His mind remained focused on science. However, a new opportunity would soon appear. A position was becoming available that would place Newton in charge of one of England's most important institutions. It would take him away from Cambridge, away from the quiet rooms where he had made his greatest discoveries, and into the center of national affairs. The next stage of Newton's life would be very different. He would become a public figure, a government official, and the guardian of the nation's currency. The scientist who had unlocked the secrets of gravity was about to face a new challenge. Could the same mind that understood the movement of planets also solve the problems of society?
Newton in London, the master of the mint.
Isaac Newton had spent much of his life surrounded by books, calculations, and quiet rooms. His world had been one of ideas, numbers, experiments, the invisible forces that shaped nature. But in 1696, Newton entered a completely different world. A world of criminals, politics, money, and national responsibility. He became warden of the Royal Mint. It was a position that many believed would be mostly ceremonial. They were wrong. Newton would approach the job with the same determination he had shown when studying the universe. The Royal Mint was responsible for producing England's coins. But the country faced a serious problem. Counterfeit money was everywhere. Fake coins were weakening trust in the economy. Many criminals had discovered ways to secretly remove small amounts of precious metal from coins and replace them with cheaper materials. This practice, known as clipping, caused enormous damage. A coin that looked valuable might contain far less silver or gold than it should. Newton immediately began investigating. He did not simply sit behind a desk. He personally examined evidence. He studied the methods used by counterfeiters. He questioned witnesses. He gathered information. The same careful mind that had analyzed planetary motion was now analyzing criminal networks. Newton discovered that counterfeiting was not a minor problem. It was organized crime. Groups of criminals were producing false coins and distributing them throughout the country. The scale of the operation shocked him. Newton decided that protecting the currency required action. He became a determined investigator. He visited taverns and meeting places where criminals operated. He collected evidence. He built cases against those responsible. Some criminals attempted to threaten him. Others tried to hide their activities. But Newton continued. The man who had calculated the movement of planets was now tracking the movement of criminals. One of the most famous cases Newton worked on involved William Chaloner. Chaloner was a skilled counterfeiter who presented himself as an expert helping the government identify fake coins. In reality, he was involved in producing them. Newton carefully gathered evidence against him. Eventually, Chaloner was convicted and executed. The victory strengthened Newton's reputation as a determined public servant. Newton also transformed the Royal Mint itself. He helped introduce improvements in coin production. The process became more secure. Coins became more reliable. Public confidence in the currency improved. In 1699, Newton became master of the mint, a position he held for the rest of his life. Unlike many scholars who struggled outside academic environments, Newton proved he could succeed in government. He brought the same qualities to administration that he brought to science. Precision, patience, attention to detail, a refusal to accept mistakes. Yet London offered Newton something else: a new social world. He met politicians, scientists, and influential figures. He became connected with a growing scientific community centered around the Royal Society. The isolated young man who once worked alone at Cambridge had become one of Britain's most respected public figures. However, his move away from Cambridge also marked a change. The period of his greatest discoveries was behind him. The years of creating calculus, the experiments with light, the development of gravity. Those achievements had already transformed human knowledge. Now Newton entered the final phase of his life. a phase focused less on discovering new laws of nature and more on defending, organizing, and expanding his legacy. But Newton's curiosity never disappeared. Even while managing the Mint, he continued studying. He investigated ancient history. He explored theology. He searched for hidden patterns in religious texts. His mind remained restless. The universe was still full of mysteries. As the 17th century came to an end, Newton stood at the peak of his reputation. He was no longer an unknown scholar. He was Sir Isaac Newton, a symbol of human intelligence, a man whose ideas had changed how people viewed reality itself. But fame came with a cost. The same intensity that had driven his discoveries also created conflicts. His relationships with other scientists became complicated. His desire for recognition remained strong. And his final years would reveal another side of the great thinker. A man not only searching for truth, but also trying to secure his place in history.
Newton and the Royal Society, becoming the voice of science.
By the beginning of the 18th century, Isaac Newton had become more than a scientist. He had become a symbol. Across Europe, scholars studied his work. Students learned his mathematics. Astronomers used his theories to predict the movements of the heavens. The man who had once hidden away in a small room at Cambridge was now recognized as the greatest scientific mind of his age. But Newton's journey toward influence was not complete. His next role would place him at the center of Britain's scientific world. The Royal Society. The Royal Society had been created to encourage the study of nature through observation and experiment. Its members believed that knowledge should come from evidence rather than tradition. They examined discoveries, discussed theories, shared experiments. It became one of the most important scientific organizations in the world. In 1703, Newton was elected president of the Royal Society. He would hold this position for the rest of his life. Leading the Royal Society gave Newton enormous influence. He controlled meetings, supported research, encouraged scientific communication. He helped shape the direction of British science. However, his leadership style reflected his personality. Newton was brilliant, but he was also determined. He expected high standards from others because he demanded the same from himself. Under Newton's presidency, the Royal Society continued to grow in importance. Scientific discoveries from across Britain and Europe were presented before its members. Experiments were performed and debated. Ideas were challenged. The process was sometimes difficult, but it pushed science forward. Newton believed that careful investigation was the path to truth. Yet Newton's leadership was not without controversy. He remained protective of his reputation. The memories of earlier disputes, especially the conflicts surrounding calculus, had left a lasting impression on him. He did not want his discoveries overlooked. He did not want others to claim achievements he believed belonged to him. One of Newton's major interests during this period was improving his earlier work. He revised optics, his famous study of light and color. Years earlier, he had demonstrated that white light was actually made of many different colors. Using a prism, he showed that sunlight could be separated into a spectrum. This challenged the common belief that color was created by objects themselves. Newton showed that color was connected to the behavior of light. His experiments with light revealed another important principle. Science was not simply about thinking. It required testing. A scientist could create a theory, but nature itself had the final answer. Newton's approach became a model for modern experimental science. As president of the Royal Society, Newton also witnessed a new generation of scientists emerging. They were building upon the foundation he had created. They studied electricity, chemistry, astronomy, mechanics. The scientific revolution that Newton helped begin continued to expand. However, despite his public success, Newton remained deeply private. He rarely spoke about his emotions. He had few close friendships. He continued working long hours. Even in old age, his curiosity remained powerful. He still searched for answers to questions that had fascinated him throughout his life. Newton had spent decades uncovering the laws that governed the physical universe. Now he was helping guide the people who would continue that search. His greatest achievement was not only the discoveries he made. It was the new way of thinking he created. A world where nature could be questioned, measured, calculated, understood. But Newton's story was far from over. Behind the public image of the famous scientist was a man still chasing mysteries. He studied ancient knowledge, explored religious writings, investigated the history of civilization. To Newton, the universe was still filled with hidden patterns waiting to be uncovered. The final decades of his life would reveal a fascinating contradiction. The same man who gave humanity the most precise scientific description of nature also spent years exploring subjects that belonged to philosophy, history, and faith. Newton was not only searching for how the universe worked. He was searching for why it existed at all. Beyond science, Newton's hidden studies and the questions of the universe. To the world, Isaac Newton was the man who explained gravity. He was the scientist who revealed the laws controlling motion, the mathematician who created calculus, the thinker who transformed humanity's understanding of nature. But behind the public image was another Newton, a man who spent thousands of hours studying subjects that he rarely discussed openly. Ancient history, religious writings, prophecy, the origins of civilization. Newton was not only interested in how the universe worked. He wanted to understand its deeper meaning. Many people imagined Newton as a purely mathematical thinker. Yet his personal writings reveal a much broader curiosity. His library contained hundreds of books covering science, philosophy, theology, and history. He studied ancient languages. He examined old manuscripts. He searched for patterns hidden within the past. To Newton, knowledge was connected. The same careful reasoning he applied to nature, he applied to human history and belief. One of Newton's greatest interests was religion. He spent years studying biblical texts and early Christian writings. He believed that understanding the past was essential for understanding truth. Newton questioned many accepted religious ideas of his time. However, he kept many of his theological opinions private because expressing certain views openly could have damaged his career. Newton also became fascinated by ancient chronology. He attempted to reconstruct the timeline of ancient kingdoms and civilizations. He compared historical records, writings, and traditions. His approach was similar to his scientific work. He gathered evidence. He analyzed sources. He searched for consistency. To Newton, the universe was not a random collection of events. It was an ordered creation. The same mind that searched for mathematical laws in the movements of planets searched for patterns in the story of humanity. He believed that hidden structures existed everywhere. Modern readers are sometimes surprised by these interests. They may expect Newton to have focused only on physics. But in Newton's time, the boundaries between science, philosophy, and theology were not as separate as they are today. Many scholars believed that studying nature was a way of discovering more about existence itself. Newton belonged to this tradition. Even while exploring these subjects, Newton continued improving his scientific reputation. A second edition of Principia was published in 1713. It included corrections, additions, and further explanations. Newton continued refining his ideas decades after his original discoveries. He was never satisfied with simply being correct. He wanted his work to be as complete as possible. By now, Newton had become a living legend. Visitors traveled to meet him. Students studied his writings. Scientists across Europe considered his ideas essential. He had achieved something almost impossible. He had changed the way humanity viewed reality. Yet the final years of Newton's life carried a strange contrast. The man who had uncovered the mathematical order of the cosmos still searched for unanswered questions. He knew more about the physical universe than anyone alive. But he remained aware of how much remained unknown. Newton once compared human knowledge to a child playing on a beach, finding a smoother pebble or prettier shell while the great ocean of truth remained unexplored. Whether or not these exact words were recorded accurately, the idea reflected something important about Newton. His genius was not only his ability to discover answers. It was his willingness to recognize mysteries. As Newton entered old age, his achievements were celebrated across Britain. He received honors. He became one of the most respected figures of his generation. But history would remember him for more than titles and awards. It would remember the questions he asked. Why do objects fall? Why do planets move? What laws connect everything? Those questions changed the future. Newton had spent his life searching for the hidden rules of existence. Now a new era was beginning. Future scientists would build upon his discoveries. They would explore electricity, atoms, energy, space, and eventually the strange worlds of relativity and quantum physics. But they would all stand on the foundation Newton created. The universe had been given a mathematical voice, and humanity had learned how to listen.
Chapter 5: The Final Years of Isaac Newton, Legacy, Death, and the Birth of Modern Science.
The last great years. By the beginning of the 18th century, Isaac Newton had become something more than a scientist. He had become a symbol of human understanding. His discoveries had transformed mathematics, physics, astronomy, and philosophy. Yet the man behind the achievements remained much the same as he had always been. Curious. Determined. Restless. Even in old age, Newton continued searching for answers. London had replaced Cambridge as Newton's home. The quiet rooms where he had once worked alone had been replaced by public recognition. He lived comfortably. He was respected by politicians, scientists, and scholars. Visitors came from across Europe hoping to meet him. To many people, Newton represented the highest achievement of human intelligence. In 1705, Newton received one of Britain's greatest honours. Queen Anne knighted him. He became Sir Isaac Newton. This was a remarkable moment. A scientist who had spent his early life studying alone in rural Lincolnshire had risen to become one of the most celebrated figures in the nation. He was the first scientist to receive this honour. But Newton's mind never stopped working. Although his greatest discoveries were behind him, he continued revising his writings. He corrected calculations, updated explanations, refined arguments. His pursuit of perfection continued throughout his life. Newton also remained deeply interested in the future of science. He understood that his work was not the end of discovery. It was the beginning of a new journey. Future generations would use his laws as a foundation. Engineers would design machines. Astronomers would explore deeper into space. Physicists would investigate the smallest pieces of matter. Newton had opened a door that others would walk through for centuries. However, age slowly began to affect him. The intense working habits of his youth had taken a toll. The long nights of study, the constant concentration, the endless search for answers. His body was growing weaker, even though his reputation continued to grow stronger. Newton's later years were filled with reflection. He looked back on a life unlike almost any other. From a difficult childhood, he had risen to become one of the most influential thinkers in history. He had changed humanity's relationship with the natural world. Before Newton, the universe was something people observed. After Newton, it was something people could calculate. His influence extended far beyond his own discoveries. The scientific method he represented encouraged people to test ideas through evidence. His mathematics provided tools for solving problems that had once seemed impossible. His laws created a framework that guided science for generations. Yet Newton understood that knowledge was never complete. The more he discovered, the more questions appeared. The universe remained vast. Mysteries remained hidden. There were still things humanity did not understand. And perhaps that was what kept Newton curious until the end. The final chapter of Newton's life was approaching. The man who had studied the movement of planets, the nature of light, and the mathematics of change would soon leave the world. But his ideas would continue moving forward. Like the planets he studied, Newton's discoveries would continue their journey long after he was gone. The death of Newton and the immortal legacy. On the evening of the 20th of March, 1727, the world began to lose one of its greatest minds. Isaac Newton was 84 years old. For most people, an 84-year life in the 18th century was extraordinary. Newton had lived through a period of enormous change. He had witnessed the transformation of science from ancient philosophy into a powerful mathematical discipline. He had not simply studied the universe. He had changed the way humanity thought about it. During his final months, Newton's health gradually declined. The energy that had once carried him through endless nights of calculation had faded. The hands that had written equations, experiments, and discoveries now rested more often. But his reputation had already become permanent. His name had moved beyond the world of scholars. It had become known throughout Europe. Newton died peacefully at his home in Kensington, London. The news spread quickly. Britain had lost one of its most celebrated citizens. Scientists, politicians, and scholars recognized that the world had changed because of him. His body was taken to Westminster Abbey, where he was buried among kings, poets, and national heroes. It was a remarkable honor. A scientist had been placed alongside the greatest figures of British history. But Newton's greatest monument was not a building. It was an idea. He had shown that the universe followed discoverable rules. Nature was not a mystery beyond human understanding. With patience, observation, and mathematics, people could uncover its secrets. The influence of Newton's work spread across the world. Engineers used his laws to design machines. Astronomers used his mathematics to understand the movement of planets and comets. Physicists built upon his ideas for generations. The Industrial Revolution that would transform society was made possible partly because Newton had provided a mathematical understanding of forces and motion. Yet Newton's story did not end with his death. His ideas continued evolving. Scientists discovered new forces, new forms of energy, new worlds beyond Earth. Each discovery added another layer to humanity's understanding of nature. More than 200 years after Newton's death, another scientist would challenge and expand his vision. Albert Einstein would show that Newton's description of gravity was not the final answer. Space and time themselves were connected. Gravity was not simply a force pulling objects together. It was the bending of the fabric of space-time. But Einstein did not replace Newton. He built upon him. Without Newton's foundation, Einstein's discoveries would have been impossible. In the 20th century, scientists would go even further. They would discover atoms, quantum mechanics, black holes, the expansion of the universe. They would send spacecraft beyond Earth and use Newton's mathematics to guide them. A person who studied falling objects beneath an apple tree had helped humanity reach other planets. Newton's greatest achievement was not one equation. It was a new way of thinking. He taught humanity to ask questions differently. Instead of accepting mystery, investigate. Instead of guessing, measure. Instead of assuming, test. His approach became one of the foundations of modern science. Looking back across centuries, Newton's life seems almost impossible. A child born into uncertainty. A young scholar working alone during a plague. A mathematician inventing new methods. A scientist revealing the laws of motion and gravity. A thinker whose ideas reached from Earth to the stars. But perhaps the most remarkable thing about Newton was not how much he discovered. It was how much he realized remained unknown. He knew the universe was larger than any single mind could understand. His curiosity never disappeared. The questions continued. And because Newton asked those questions, humanity began a journey that continues today. The story of Isaac Newton was not only the story of one man. It was the story of a turning point in human history. A moment when humanity learned that the universe was not silent. It was speaking through mathematics, and Newton had discovered part of its language.
Chapter 6: Newton's World and the Scientists Who Followed.
Part 1: The Universe after Newton. When Isaac Newton died in 1727, he left behind more than books and equations. He left behind a new way of seeing reality. For thousands of years, humans had looked at the universe with curiosity and wonder. They watched the stars move across the sky, observed the changing seasons, and wondered about the forces that shaped the world. Newton transformed those questions into mathematics. He showed that the universe was not simply a collection of mysterious events. It was a system governed by laws. For the first time, scientists possessed a framework that could explain both Earth and the heavens. A falling stone and an orbiting planet were no longer separate mysteries. They were connected by the same principles. Newton had united the sky and the ground. The universe had become one enormous mathematical machine. The influence of Newton's ideas spread rapidly. Universities across Europe began teaching his theories. Scientists studied his laws. Engineers applied his mathematics to practical problems. A new generation of thinkers grew up in a world shaped by Newton's discoveries. One of the first great figures to continue Newton's work was the French mathematician and physicist Émilie du Châtelet. She recognized the importance of Newton's ideas and helped introduce them to continental Europe. At a time when many women were excluded from scientific institutions, she made significant contributions to understanding and explaining Newtonian physics. Her work helped spread Newton's ideas beyond Britain. Another important figure was Leonhard Euler. Euler expanded mathematics into new areas and used Newton's principles to explore mechanics, astronomy, and motion. His equations became some of the most powerful tools in science. The mathematical language created during Newton's time continued to grow. Astronomers also used Newton's theories to explore the solar system. The movements of planets could now be predicted with extraordinary accuracy. Comets, once seen as mysterious signs in the sky, became objects that could be studied mathematically. The heavens were no longer unreachable. They were becoming understandable. Newton's influence also changed philosophy. Thinkers began asking new questions about humanity's place in nature. If the universe followed mathematical laws, what did that mean for life, consciousness, and free will? Science was no longer only about explaining objects. It had become a way of understanding existence itself. However, Newton's universe was not the final answer. His laws worked brilliantly for everyday objects and planetary motion. They could predict eclipses, calculate trajectories, and guide engineering. But as scientists explored deeper, they discovered situations where Newton's ideas were incomplete. The first signs appeared when people studied electricity, light, and the tiny building blocks of matter. The universe was proving to be stranger than anyone had imagined. Invisible forces existed. Particles behaved in unexpected ways. Light refused to fit neatly into old explanations. Still, Newton's foundation remained essential. Every new discovery began by standing upon what came before. Science was not a collection of isolated breakthroughs. It was a chain. Each generation inherited knowledge from the previous one and pushed further. Newton had started the chain. The question now was, how far could humanity travel using the road he had built? The next centuries would reveal discoveries that Newton himself could never have imagined. Electricity, atoms, machines, computers, space travel, and eventually a universe far stranger and more beautiful than even Newton had dreamed. Part 2: The Age of Discovery, Electricity, Industry, and the Expanding Universe. Newton had revealed the laws of motion. He had explained gravity. He had shown that mathematics could unlock the secrets of nature. But the universe still held countless mysteries. The centuries after Newton would bring discoveries that would transform the world in ways he could never have imagined. The age of mechanics would become the age of electricity, technology, and exploration. During Newton's lifetime, most machines were simple. Human and animal power drove work. Water wheels and windmills provided energy. Transportation depended on horses and sailing ships. But Newton's understanding of forces created the foundation for a new technological age. Scientists and engineers began applying mathematical principles to practical inventions. The Industrial Revolution began changing society. Machines became larger and more powerful. Factories appeared. Steam engines transformed transportation and manufacturing. The ideas of motion, force, and energy that Newton had helped establish became essential tools for engineers. A world built upon Newton's mathematics was beginning to emerge. But another mystery was waiting. Electricity. People had known about static electricity for centuries, but nobody understood its true nature. Small experiments with sparks and charged objects hinted that another invisible force existed in the universe. A force different from gravity. Scientists such as Michael Faraday began exploring electricity and magnetism. Faraday discovered that changing magnetic fields could create electric currents. This discovery would eventually lead to generators, electric motors, and modern power systems. The world was discovering that invisible forces controlled much more than planetary motion. Then came James Clerk Maxwell. Building upon the discoveries of others, Maxwell created mathematical equations describing electricity and magnetism. His work revealed something astonishing. Light itself was an electromagnetic wave. The colors Newton had studied with his prism were connected to a much deeper structure of the universe. Newton had studied light. Maxwell revealed its hidden mathematical nature. The 19th century also brought discoveries about atoms and matter. Scientists began investigating what everything was made from. Were materials continuous? Or were they built from tiny pieces? The ancient idea of atoms became a scientific theory. The universe was becoming smaller as scientists looked deeper. At the same time, astronomers were looking further outward. New telescopes revealed distant stars, galaxies, and strange objects in the depths of space. Humanity's view of the universe expanded. The solar system was no longer the entire story. Earth was one small world among countless others. Yet Newton's influence remained everywhere. His laws still guided engineers. His mathematics still predicted planetary motion. His ideas continued to provide the framework for understanding the physical world. But scientists were discovering that reality contained layers Newton had never encountered. By the beginning of the 20th century, the universe was preparing to reveal its greatest surprises. Space and time were not as simple as Newton believed. Light behaved in unexpected ways. The smallest particles followed strange rules. The universe was about to enter a new scientific revolution. And standing at the doorway of that revolution was a young physicist who would challenge humanity's understanding of space, time, and gravity. His name was Albert Einstein. But before Einstein could transform physics, he would first have to understand the giant whose shadow covered science for more than 200 years. Isaac Newton. Part 3, Einstein meets Newton, the beginning of a new universe. For more than 2 centuries, Isaac Newton's vision of the universe stood as the greatest achievement in science. His laws explained motion. His theory of gravity explained the planets. His mathematics provided a framework that seemed almost complete. Scientists believed they understood the basic structure of reality. Space was a stage. Time was a universal clock. Objects moved through this fixed universe according to Newton's laws. But nature had been hiding deeper secrets. At the beginning of the 20th century, a young scientist began asking questions that challenged everything people thought they knew. His name was Albert Einstein. Like Newton, Einstein was fascinated by the hidden rules of the universe. He was not satisfied with simply accepting existing explanations. He wanted to understand the principles beneath them. One of Einstein's first questions involved light. Newton had studied light centuries earlier and discovered that white light contained many colors. Later scientists discovered that light behaved like a wave. But something did not make sense. According to Newton's ideas, speed should simply add together. If someone ran forward while throwing a ball, the ball's speed would combine with the runner's speed. But what happened with light? Would light moving from a moving object travel faster? Experiments suggested something impossible. Light always seemed to travel at the same speed. Einstein realized that the problem was not with the experiments. The problem was with the old understanding of space and time. Perhaps space and time themselves were not fixed. Perhaps they changed depending on how an observer was moving. In 1905, Einstein published his theory of special relativity. It introduced a completely new picture of reality. Time was not universal. Different observers could experience time differently. Distances could change depending on motion. The universe was far stranger than Newton had imagined. But Einstein did not see himself as destroying Newton's work. Newton had been correct within the conditions people experienced every day. A moving car. A falling object. A planet orbiting a star. Newton's equations remained incredibly accurate. Einstein simply revealed that Newton's laws were part of a larger picture. The greatest challenge was gravity. Newton described gravity as a force acting between objects. Einstein asked a deeper question. What if gravity was not a force at all? What if massive objects changed the shape of space itself? After years of work, Einstein developed general relativity. Gravity was no longer viewed as an invisible pull. Instead, massive objects such as stars and planets curved the fabric of space-time. Earth did not orbit the Sun because it was being pulled by an invisible rope. It followed a path through curved space-time created by the Sun's immense mass. This was a breathtaking new vision. Newton had discovered the mathematics of gravity. Einstein discovered the geometry of gravity. Two great minds separated by centuries had looked at the same universe and uncovered different layers of truth. The relationship between Newton and Einstein represents one of the greatest stories in science. Newton built the foundation. Einstein expanded the building. Neither cancelled the other. Together, their ideas created a deeper understanding of reality. Yet even Einstein's universe was not the final answer. The 20th century would reveal another mystery. At the smallest scales of nature, particles behaved in ways that seemed impossible. The universe was not only curved. It was also uncertain. A new revolution was beginning. Quantum physics. And once again, humanity would discover that reality was stranger than anyone had imagined. Part 40: Quantum Reality, the universe beyond Newton and Einstein. Newton had revealed the grand architecture of the universe. Einstein had shown that space and time themselves could bend. But as scientists looked deeper into nature, they discovered a hidden world that followed rules unlike anything they had experienced before. The world of atoms. The world of particles. The world of quantum physics. For centuries, scientists believed that if they knew enough information about an object, they could predict exactly what would happen next. Newton's universe seemed to support this idea. If you knew the position and speed of a planet, you could calculate its future path. The universe appeared predictable. But the tiny world inside atoms challenged this belief. At the beginning of the 20th century, scientists discovered that atoms were not the smallest pieces of reality. Inside atoms were even smaller particles. Electrons, protons, neutrons, and eventually, many more. The deeper scientists looked, the more complicated nature became. One of the first mysteries involved light. Scientists discovered that light could behave like a wave. But experiments also showed that light could act like a stream of particles called photons. It seemed impossible. How could something be both a wave and a particle? The answer required a completely new way of thinking. Scientists such as Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and Owen Schrödinger helped develop quantum theory. They discovered that at the smallest scales, nature did not behave like the familiar world around us. Particles did not always have definite positions. Events could only be described through probabilities. This was one of the greatest challenges to Newton's vision. Newton had imagined a universe controlled by precise laws. Quantum physics revealed a universe where uncertainty was built into nature itself. At the atomic level, reality was not a perfectly predictable machine. It was something stranger. Werner Heisenberg introduced the uncertainty principle. It showed that certain pairs of properties, such as a particle's position and momentum, could not both be known with unlimited accuracy. The more precisely one was measured, the less certain the other became. Nature itself placed limits on knowledge. Einstein struggled with some of these ideas. He believed the universe should contain deeper hidden rules. He famously questioned the randomness of quantum mechanics, suggesting that nature could not be based purely on chance. However, experiments continued to support quantum theory. The universe appeared to contain uncertainty at its foundations. Yet quantum physics did not replace Newton or Einstein. Like Einstein expanded Newton, quantum physics expanded Einstein. Each theory described a different part of reality. Newton explained everyday motion. Einstein explained gravity, space, and time. Quantum theory explained the microscopic world. Together, these discoveries created a much larger picture of the universe. A universe of galaxies and black holes. A universe of atoms and particles. A universe where the very nature of reality was more mysterious than anyone had imagined. The journey that began with Newton studying an apple had reached the smallest building blocks of existence. His question had been simple. What laws govern the universe? Centuries later, humanity was still searching for the answer. But science continued moving forward. New technology allowed humans to see further into space and deeper into matter. Telescopes became more powerful. Computers became more advanced. Machines began exploring places humans could never reach. Newton could never have imagined the modern world. Satellites orbiting Earth. Robots exploring other planets. Artificial intelligence analyzing information. Spacecraft traveling beyond the solar system. Yet all of these achievements rested upon the foundations he helped create. The story of Newton was no longer only about one man. It had become the story of humanity's greatest adventure. The search to understand reality itself. Part 5, From Newton's Apple to Space Exploration, the Universe in the Modern Age. Isaac Newton once looked at a falling apple and wondered about the invisible force pulling it toward the Earth. More than 3 centuries later, humanity would use Newton's ideas to leave the Earth entirely. The question that began beneath an apple tree would eventually lead to rockets, satellites, and journeys across the solar system. Newton had shown that objects moved according to mathematical laws. This meant that if scientists understood enough about motion and gravity, they could predict the paths of objects through space. That idea became the foundation of space exploration. A spacecraft traveling to another planet was not simply launched into the sky. Its journey was calculated. Its speed, direction, and path were carefully designed using the same principles Newton discovered. In the 20th century, rocket science transformed humanity's relationship with space. Scientists learned that rockets could overcome Earth's gravity by producing enormous thrust. Newton's third law of motion explained why. A rocket pushes gases downward, and the gases push the rocket upward. A principle discovered centuries earlier became the key to reaching the stars. In 1957, humanity entered a new era when the first artificial satellite was placed into orbit around Earth. The night sky was no longer filled only with natural objects. Human creations had joined the planets and stars. Newton's vision of a mathematical universe had become a technological reality. In 1969, humans achieved what had once seemed impossible. Astronauts traveled to the moon. The journey depended on precise calculations of gravity, motion, and orbital paths. The moon that Newton had studied from Earth was now a place humans could visit. The distance between imagination and reality had become smaller. Space exploration continued. Robotic spacecraft traveled to distant planets. Telescopes looked deeper into the universe than ever before. Satellites studied Earth's climate, weather, and environment. Every mission relied upon centuries of scientific progress. Newton had provided one of the first great steps. But modern science also revealed something Newton could never have known. The universe was not only a place of predictable motion. It was a place of enormous complexity. Galaxies were billions of light years away. Black holes warped space and time. Dark matter and dark energy suggested that much of the universe remained mysterious. The search for knowledge continued. Scientists were still asking the same type of questions Newton asked. What forces shape the universe? What rules govern reality? What secrets remain hidden? Today, advanced computers allow scientists to simulate galaxies, model climate systems, and analyze enormous amounts of information. Artificial intelligence helps researchers discover patterns that would be impossible for humans to find alone. Technology has become another tool in humanity's search for understanding. Yet the spirit remains the same as Newton's. Observe. Question. Experiment. Discover. The tools have changed, but the curiosity has not. The story that began with one person studying gravity became the story of an entire species exploring existence. Newton did not give humanity all the answers. He gave humanity a method for finding them. From the falling apple to the spacecraft among the planets, the journey has always been driven by the same desire: to understand the universe we inhabit. And the journey is still continuing. Chapter 7: The Hidden Newton, the Man Behind the Genius. Part 1: Beyond the Legend. History remembers Isaac Newton as a towering figure. A genius. A discoverer. A man who unlocked the secrets of gravity and changed humanity's understanding of the universe. But behind the famous portrait was a much more complicated person. Newton was not simply a brilliant mind working alone in perfect harmony. He was a human being. He had fears, doubts, conflicts, and a personality filled with contradictions. To understand Newton completely, we must look beyond the discoveries and discover the man himself. The popular image of Newton often begins with the apple. A quiet scientist sitting beneath a tree. An apple falls. A sudden flash of inspiration reveals gravity. The story has become one of the most famous moments in scientific history. But real discoveries are rarely so simple. Newton's understanding of gravity came from years of mathematical work, observation, and careful thought. The apple may have represented the beginning of a question. But the answer required a lifetime of effort. Newton was born on Christmas Day in 1642 according to the old Julian calendar used in England at the time. He entered the world prematurely and was considered unlikely to survive. His early life was marked by difficulty. His father died before he was born. When Newton was still young, his mother remarried and left him in the care of his grandmother. The experience affected him deeply. As a child, Newton was not known as a natural leader. He was quiet, often isolated. He preferred creating things and thinking deeply rather than joining ordinary childhood activities. He built models, designed mechanical devices, studied how things worked. His imagination was always active. At school, Newton was not initially considered exceptional. However, something changed. He became intensely competitive. After being bullied by another student, Newton challenged himself to become better. His desire to improve pushed him forward. The quiet child began developing the determination that would define his entire life. Newton's greatest strength was his ability to focus. When he became interested in a subject, everything else disappeared. He could spend days thinking about a single problem. He could ignore food, sleep, and conversation while searching for an answer. This intense concentration allowed him to achieve extraordinary things. But the same intensity also created difficulties. Newton struggled with relationships. He often found it hard to trust people. He kept his emotions private. He could be suspicious of others' intentions. The qualities that made him a great investigator sometimes made ordinary life challenging. Newton lived during a time of enormous change. The world was moving away from ancient explanations and toward modern science. Old beliefs were being questioned. New discoveries were appearing. The telescope had revealed new worlds. Mathematics was becoming more powerful. Experiments were replacing assumptions. Newton became one of the greatest figures of this transformation. Yet Newton himself was always searching. Even after explaining gravity, he continued asking questions. What was light? What were the laws behind nature? What was the structure of the universe? He never saw knowledge as complete. Perhaps this was Newton's greatest quality. Not that he knew everything, but that he understood how much remained unknown. His curiosity pushed him beyond ordinary limits. It allowed him to see connections others missed. The hidden Newton was not just the man who discovered gravity. He was a child who survived uncertainty. A young thinker who questioned everything. A scientist who transformed the world. And a human being whose complexity made his achievements even more remarkable. In the next part, we will explore Newton's personality, his unusual habits, and the mysterious private world that existed behind his public success. Part 2. The strange habits and secret world of Isaac Newton. The world saw Isaac Newton as a great scientist. A professor. A mathematician. The man who explained gravity. But those who knew him personally saw something different. They saw a man of unusual habits, extraordinary focus, and a mind that seemed permanently connected to ideas beyond ordinary life. Newton was not like most people. His way of thinking was unique. His way of living was often just as unusual. Newton's greatest companion throughout his life was his own curiosity. When a question entered his mind, it rarely left. He could become completely absorbed by a problem. Hours would disappear. Then days. Sometimes even years. A normal person might set a difficult question aside and return later. Newton often could not. The problem followed him everywhere. During his years at Cambridge, Newton developed a reputation for working alone. While other students socialized, attended gatherings, or enjoyed university life, Newton preferred his room and his books. He was not interested in popularity. He was interested in understanding. His world was filled with calculations, experiments, and ideas. Newton's notebooks reveal the intensity of his thinking. He recorded observations about light, experiments with chemicals, mathematical discoveries, questions about philosophy and religion. His interests covered almost every area of knowledge available during his lifetime. Nothing seemed too small to investigate. His experiments with light showed his unusual determination. Newton did not simply read about color. He wanted to discover what color truly was. He passed sunlight through glass prisms. He darkened rooms. He carefully observed the results. He repeated experiments again and again. Through patience, he discovered that white light was actually a mixture of colors. Newton also experimented on himself. In his investigations of vision and light, he once studied the effects of pressure on his own eye. He was willing to risk discomfort to answer scientific questions. His desire for knowledge could overcome his concern for himself. His working habits were extreme. He often forgot meals. He sometimes slept very little. He could become so focused that he lost track of time completely. Visitors described moments when Newton appeared unaware of his surroundings because his thoughts were somewhere else. However, Newton also had a more secretive side. He kept many of his writings private. Thousands of pages remained unpublished during his lifetime. Some contained scientific ideas. Others explored subjects that he believed were too controversial to share openly. One of these hidden interests was alchemy. Today, alchemy is often associated with attempts to turn ordinary metals into gold. But during Newton's time, it was a serious area of investigation. Many scholars believed chemistry might contain deeper secrets about matter. Newton studied ancient texts and conducted experiments searching for a better understanding of nature. To Newton, there was no sharp separation between science and mystery. The same universe that followed mathematical laws also contained unanswered questions. He believed nature had hidden structures waiting to be discovered. His personality could also be difficult. Newton could be generous and supportive, but he could also hold grudges for many years. Arguments affected him deeply. Scientific disagreements became personal battles. His conflict with other thinkers often lasted far longer than necessary. Yet these imperfections make Newton more fascinating. He was not a perfect symbol carved from stone. He was a real person. A person with extraordinary abilities and ordinary human weaknesses. The genius who discovered gravity was also the man who struggled with trust. The mathematician who created new worlds of knowledge was also someone who spent much of his life searching for certainty. Perhaps Newton's greatest secret was that his genius came from the same place as his struggles. He could not stop questioning. He could not stop searching. He could not accept simple answers. Part 3: Newton's experiments with light, seeing the invisible universe. Before Isaac Newton became famous for gravity, before his name became connected with the movement of planets, he was fascinated by something far closer. Light. Everyday people saw sunlight. They saw colors. They saw reflections in mirrors and shadows on walls. But nobody truly understood what light was. Newton decided that the only way to find out was to investigate it himself. In the 17th century, many people believed that color was created by objects. A red flower was thought to contain redness. A blue sky was thought to contain blueness. Newton suspected something different. Perhaps color was not created by objects. Perhaps color was hidden within light itself. To test this idea, Newton performed one of his most famous experiments. He entered a dark room and allowed a narrow beam of sunlight to pass through a glass prism. As the light traveled through the prism, something remarkable happened. The white beam separated into a band of colors. Red, orange, yellow, green, blue, indigo, violet. A rainbow appeared on the wall. Many people before Newton had seen this effect. But Newton asked a deeper question. Was the prism creating the colors? Or was it revealing colors that already existed inside the sunlight? To answer this, Newton designed another experiment. He placed a second prism in the path of one separated color. If the prism created color, the second prism should change it again. But it did not. The single color remained the same. Newton had discovered that white light was not pure. It was a mixture of different colors combined together. This was a revolutionary idea. Light, something that seemed simple and ordinary, was actually far more complex. The world contained hidden structures that human senses alone could not reveal. Newton had shown that careful experiments could uncover realities invisible to everyday experience. His discoveries changed the understanding of optics forever. He explained why objects appeared to have different colors. He studied reflection and refraction. He investigated how lenses behaved. His work became the foundation for modern optical science. Newton's research into light also led him to build a new type of telescope. The telescopes of his time used lenses. But lenses created problems. They could distort colors, causing blurred images. Newton realized that mirrors could provide a better solution. He created the first practical reflecting telescope. Instead of using glass lenses to gather and focus light, it used a curved mirror. This design reduced color distortion and allowed astronomers to observe the heavens more clearly. The telescope revealed Newton's connection between the smallest and largest scales of nature. The same person who studied tiny rays of light also studied enormous planets. The same mind that explored color explored the cosmos. Newton's work with light also raised deeper questions. What exactly was light? Was it a stream of tiny particles? Was it a wave? Newton supported the idea that light consisted of particles. Later scientists would discover that light had both wave-like and particle-like properties. The mystery Newton explored would continue for centuries. His studies of light demonstrated one of the most important principles of science. A simple observation can lead to a completely new understanding of reality. A beam of sunlight entering a dark room became a doorway into the hidden structure of nature. Newton had learned that the universe contained secrets everywhere, A falling object revealed gravity. A beam of light revealed color. A moving planet revealed mathematics. The ordinary world was filled with extraordinary mysteries. The scientist who looked beyond the obvious changed the way humanity saw not only the universe above us, but the very light that allows us to see it. Curiosity made everyday life difficult, but it also allowed him to see the universe in a way nobody had seen before. Behind the famous portrait was not just a scientist. There was an explorer of ideas. A person who spent his entire life searching for the hidden rules of existence. Part 4: Newton's mathematics, the language behind reality. Isaac Newton once said that nature was written in the language of mathematics. To him, numbers were not simply tools for calculation. They were the hidden grammar of the universe. Behind the movement of planets. Behind the fall of objects. Behind the changing patterns of nature. Newton believed mathematics revealed the rules that controlled everything. Before Newton, mathematics was already a powerful subject. Ancient thinkers had developed geometry. Astronomers had created methods for predicting movements in the sky. But many problems remained impossible to solve. Nature was constantly changing. Objects moved. Planets traveled along paths. Quantities increased and decreased. Traditional mathematics struggled to describe these continuous changes. Newton needed a new tool. So he created one. A method he called the method of fluxions. Today, we know this area of mathematics as calculus. Calculus allowed scientists to study change itself. Instead of only asking, "Where is an object?" mathematicians could ask, "How is its position changing? How fast is it moving? How is that movement changing?" This opened a completely new way of understanding the universe. Imagine watching a spacecraft traveling through space. At any moment, it has a position. But it also has a direction. It has a speed. And that speed can itself be changing. Calculus allows scientists to describe these changing conditions with precision. Newton developed calculus while searching for solutions to problems in physics. He was not creating mathematics simply for the beauty of numbers. He needed a language powerful enough to describe motion. The universe was not static. Everything was changing. Mathematics needed to change too. However, Newton was not the only person to develop calculus. At almost the same time, the German mathematician Gottfried Wilhelm Leibniz created his own version. Leibniz developed a different system of symbols and methods. His notation eventually became the foundation used by most mathematicians today. The disagreement over priority became one of the most famous conflicts in scientific history. Newton's supporters argued that he had discovered calculus first. Leibniz supporters argued that he had developed it independently. The dispute became bitter. Modern historians generally recognize that both men made independent contributions. Newton developed powerful mathematical ideas. Leibniz created a clearer notation system that helped calculus spread. The mathematics of today carries the influence of both. Newton's mathematical achievements extended far beyond calculus. He developed methods for solving equations. He studied infinite series. He created techniques that helped transform mathematics into a more powerful science. But perhaps Newton's greatest mathematical achievement was not a single formula. It was the connection he created between mathematics and reality. Before Newton, mathematics was often viewed as a description of patterns. After Newton, mathematics became a tool for discovering the laws of nature. This idea changed science forever. The universe could be measured. Predictions could be made. Experiments could be tested. A theory was not complete until mathematics could describe it. Centuries later, Einstein would use mathematics to describe space-time. Quantum physicists would use mathematics to describe the behavior of tiny particles. Modern technology would use mathematics to create computers, satellites, and artificial intelligence. All of these developments followed the path Newton helped create. Newton's genius was not only that he knew mathematics. It was that he understood mathematics as a bridge between human thought and the universe itself. Numbers became a way of asking nature questions. Equations became a way of receiving answers. The hidden Newton was not simply a man who calculated. He was a translator. He took the silent movements of the universe and turned them into a language humanity could understand. Part 5: Newton's greatest rivalries, genius, conflict, and the search for recognition. Isaac Newton is remembered as one of the greatest scientists who ever lived. But greatness does not always come peacefully. Behind the discoveries and achievements was a man who fought many battles. Some were battles against nature itself. Others were battles against other brilliant minds. Newton wanted to understand the universe. But he also wanted the world to understand that he had been the one who discovered its secrets. Newton's competitive nature appeared early in his career. He did not simply want to solve problems. He wanted to solve problems that nobody else could solve. When he found an answer, he wanted that answer to be recognized. This drive pushed him toward extraordinary achievements. But it also created conflicts. One of Newton's greatest rivalries was with Robert Hooke. Hooke was a brilliant scientist and inventor. He made important discoveries in physics, astronomy, and microscopy. He was also a member of the Royal Society. Like Newton, Hooke was interested in understanding forces and motion. The disagreement between Newton and Hooke centered partly around gravity. Hooke suggested that planets might be influenced by an attractive force from the Sun. Newton later developed the complete mathematical theory of universal gravitation. The two men disagreed over who deserved credit for the ideas that led toward this discovery. Their relationship became increasingly difficult. Newton disliked criticism, and Hooke was known for challenging the ideas of others. Their personalities often clashed. The disagreement showed an important truth about science. Discoveries are often built by many people, but recognition is frequently contested. Newton also had a complicated relationship with Gottfried Wilhelm Leibniz. Their dispute over calculus became one of the most famous scientific arguments in history. Both men were extraordinary mathematicians. Both believed they deserved recognition. The conflict continued for years and damaged relationships between British and European mathematicians. Yet rivalry was not always harmful. Competition pushed Newton to improve his work. When challenged, he defended his ideas more carefully. When criticized, he examined his arguments more deeply. The desire to prove himself became a source of motivation. However, Newton's need for recognition also revealed his vulnerabilities. He could be deeply affected by disagreement. Criticism could feel like a personal attack. He sometimes responded more strongly than the situation required. This was the contradiction of Newton. The same intensity that allowed him to discover the laws of nature also made personal conflicts difficult. His mind was built for solving problems. But human relationships could not always be solved like mathematical equations. Despite these conflicts, Newton's achievements remained undeniable. Even those who disagreed with him recognized the power of his discoveries. His theories transformed science. His mathematics changed how people understood reality. The rivalry surrounding Newton also reveals something important about scientific progress. Science is not created by perfect people. It is created by curious people. People who argue. People who make mistakes. People who challenge one another. Newton's legacy is not weakened by his imperfections. Instead, it becomes more human. He was not a distant genius without emotions. He was a person driven by curiosity, ambition, and an extraordinary desire to understand. The hidden Newton was a man of contrasts. A private thinker who became famous. A peaceful observer who fought fierce battles. A humble explorer of nature who wanted recognition for his discoveries. His greatest rivalry, however, was not with another scientist. It was with the unknown itself. The universe was filled with unanswered questions. And Newton spent his entire life trying to uncover them.
Chapter 8: Newton's greatest discoveries explained: gravity, motion, light, and mathematics.
Part 1. The force that holds the universe together, gravity. Among all of Isaac Newton's discoveries, none has captured the human imagination more than gravity. Every person on Earth experiences it. Every object we touch is affected by it. Yet before Newton, nobody had explained its true nature. Why do objects fall? Why does the moon orbit Earth? Why do planets follow predictable paths around the sun? These questions had puzzled humanity for centuries. Newton provided the answer. The idea of gravity began with a simple observation. Objects fall toward the Earth. A stone released from a hand drops downward. Rain falls from clouds. A thrown object eventually returns to the ground. But Newton realized something extraordinary. The force pulling an apple downward might be the same force keeping the moon in orbit. This was a revolutionary idea. Before Newton, many people believed the heavens followed different rules from Earth. Earth was imperfect and changing. The sky was considered a separate, perfect realm. Newton united them. The same laws that controlled a falling object also controlled the movement of planets. Newton described gravity as a universal attraction between all objects with mass. Every piece of matter attracts every other piece of matter. The Earth attracts the moon. The moon attracts the Earth. The sun attracts the planets. Even two small objects on Earth exert a tiny gravitational pull on each other. The strength of gravity depends on two things. First, the amount of matter involved. A larger object has greater gravitational influence. This is why the sun dominates the solar system. Its enormous mass controls the paths of planets. Second, gravity weakens with distance. The farther apart objects are, the weaker the attraction becomes. Newton expressed this relationship mathematically through his law of universal gravitation. This equation allowed scientists to calculate the movement of celestial bodies with remarkable accuracy. The universe was no longer simply something to observe. It was something that could be predicted. Gravity explained the motion of the moon. The moon is constantly falling toward Earth. But because it is also moving forward through space, it continually misses the Earth. The result is an orbit. A perfect balance between falling and moving forward. Newton's gravity also explained tides. The moon's gravitational pull affects Earth's oceans. As the Earth rotates, the oceans respond to these changes, creating the rising and falling patterns we experience as tides. The power of Newton's theory was its simplicity. One idea explained countless events. A falling apple. A spinning planet. A distant comet. All connected by the same invisible force. But Newton himself understood that gravity was still mysterious. He could describe how gravity worked. He could calculate its effects. But he did not know exactly why objects attracted each other. That deeper question would remain for future generations. More than 200 years later, Albert Einstein would offer a new explanation. Gravity was not simply a force pulling objects together. It was the result of massive objects changing the shape of space and time. Yet even Einstein's theory began with Newton's discovery. Newton had found the first great clue. Gravity remains one of the greatest examples of Newton's genius. He looked at something everyone experienced. Something ordinary. Something people had ignored for thousands of years. And he discovered that hidden within it was one of the deepest secrets of the universe. Part 2. Newton's 3 laws of motion, the rules behind everything that moves. Every moment of our lives is filled with motion. A car traveling along a road. A bird flying through the sky. A person walking across a room. The Earth itself moving through space. Before Isaac Newton, people observed motion, but they did not truly understand the rules behind it. Newton changed that. He discovered that movement followed clear mathematical principles. These principles became known as Newton's 3 laws of motion. Together, they created a new understanding of how the universe moves. The first law, the law of inertia. Newton's first law revealed something surprising. Objects do not naturally stop moving. They stop because something interferes. Before Newton, many believed that motion required a continuous force. If you pushed a cart, they thought, the cart moved because of the push. When the push disappeared, the movement disappeared. Newton showed this was not true. An object at rest remains at rest unless a force acts upon it. An object in motion continues moving at the same speed and direction unless another force changes it. This property became known as inertia. Imagine a spacecraft traveling through deep space. Once its engines stop firing, it does not suddenly stop. With almost no resistance, it continues moving. The spacecraft does not need a constant force to keep going. Newton's first law explains why. The second law, force creates change. Newton's second law explained how forces affect motion. A stronger force creates greater acceleration. A heavier object requires more force to accelerate. The relationship became one of the most famous equations in science. Force equals mass times acceleration. This simple equation transformed physics. It allowed scientists to calculate how objects would move. Engineers could design machines. Astronomers could predict planetary movements. Scientists could understand collisions and impacts. Consider pushing two objects. A small ball and a heavy truck. The same force applied to both will produce very different results. The ball moves easily. The truck barely changes. The difference is mass. Newton had discovered the mathematical connection between force, movement, and matter. The third law, action and reaction. Newton's third law revealed a hidden balance in nature. Every action creates an equal and opposite reaction. When you walk, your foot pushes backward against the ground. The ground pushes you forward. When a rocket launches, it forces hot gases downward. The gases push the rocket upward. This law explains countless events. Swimming, flying, driving, jumping, even the movement of spacecraft through the emptiness of space. Together, Newton's three laws created a complete framework for understanding motion. They explained events on Earth. They explained machines. They explained the movement of objects across the universe. The importance of Newton's laws cannot be overstated. They changed science from observation into prediction. Instead of simply describing what happened, scientists could calculate what would happen next. For more than 2 centuries, Newton's laws remained the foundation of physics. Even today, engineers use them to design buildings, vehicles, aircraft, and spacecraft. They remain accurate for the world we experience every day. But Newton's laws also revealed something deeper. The universe was not chaotic. It followed patterns. Behind every movement was a reason. Behind every action was a reaction. Behind every change was a mathematical relationship. Newton had discovered the rules of motion. But he had also discovered something greater. The universe could be understood. Part 3, Newton and the nature of light, unlocking the colors of the universe. Light is one of the most familiar things in existence. Every sunrise, every star in the night sky, every color we see. Yet for thousands of years, people did not understand what light truly was. Isaac Newton was one of the first people to reveal that light contained hidden complexity. Before Newton's experiments, many scientists believed that white light was pure. They thought color was created when light interacted with objects. A red object was red because it somehow added redness to ordinary light. Newton questioned this explanation. He believed the answer was hidden within the light itself. In his famous prism experiments, Newton allowed a narrow beam of sunlight to pass through glass. The result amazed him. The white light separated into a spectrum of colors: red, orange, yellow, green, blue, indigo, violet. The important discovery was that the prism was not creating the colors. It was revealing them. White light was actually a combination of many different colors traveling together. The rainbow was not produced by nature adding colors to sunlight. It was nature separating the colors already there. Newton proved this by performing further experiments. He took one color from the spectrum and passed it through another prism. Instead of changing into new colors, it remained the same. This showed that each color had its own properties. Newton's discovery transformed the science of optics. Light was no longer something simple and mysterious. It became something that could be measured, tested, and understood. His work also improved telescopes. The telescopes of Newton's time used lenses, but lenses created problems. Different colors of light bent by different amounts, causing blurry images. Newton solved this by designing a reflecting telescope. Instead of using lenses alone, it used mirrors to collect light. This invention allowed astronomers to see the heavens more clearly. Newton's study of light helped humanity explore the universe beyond Earth. However, Newton's ideas about light were only part of the story. He believed light was made of tiny particles. Later experiments showed that light also behaved like a wave. Eventually, scientists discovered that light has a dual nature. It can behave as both waves and particles. This surprising discovery connected Newton's work with modern physics. The light Newton studied with a simple prism would eventually lead scientists toward quantum theory. A question about colors became a question about the fundamental nature of reality. Newton's experiments with light revealed an important lesson. The universe often hides its greatest secrets inside ordinary things. A beam of sunlight entering a dark room. A color appearing on a wall. A simple experiment with glass. From these small observations came discoveries that changed humanity forever. Newton had already uncovered the laws of motion and gravity. Now he had shown that even light itself contained hidden worlds waiting to be discovered. The universe was not only moving according to mathematical laws. It was shining with them. Part for Newton's mathematics, the equations that changed the world. Isaac Newton's discoveries were not only about physical objects. They were also about the language used to describe reality. That language was mathematics. Newton understood something profound. The universe was not random. Behind the movement of planets, the fall of objects, and the changing patterns of nature were relationships that could be expressed through numbers. Before Newton, mathematics was already an important part of science. Ancient civilizations had used geometry to measure land, build structures, and study the stars. Astronomers had created methods for predicting eclipses and tracking planets. But many problems remained beyond human ability. The difficulty was change. The universe was constantly moving. A planet did not stay in one place. A thrown object did not have one fixed position. A river did not have one unchanging flow. Traditional mathematics could describe shapes and quantities, but it struggled to explain continuous movement. Newton needed a new mathematical tool. That tool became calculus. Newton developed his own method, which he called the method of fluxions. It allowed him to describe how things changed from one moment to the next. Calculus introduced powerful new ideas. A scientist could calculate not just where something was, but how quickly it was changing. They could measure speed, acceleration, growth, decline. Movement itself became something mathematics could capture. This was essential for Newton's physics. Without calculus, his laws of motion and gravity would have been far more difficult to express. The planets moved along complex paths. Objects accelerated as they fell. Forces created changes over time. Calculus provided the language to describe these processes. Newton's mathematics transformed science because it connected abstract numbers with the physical universe. An equation was no longer just a collection of symbols. It became a description of reality. Imagine looking at the moon. To ancient observers, it was a mysterious object moving across the sky. To Newton, it was a body following mathematical rules. Its orbit could be calculated. Its movement could be predicted. The heavens had become measurable. Newton also contributed to other areas of mathematics. He developed methods for solving difficult equations. He explored infinite series. He created techniques that would influence mathematicians for generations. However, Newton's mathematical achievements were not created in isolation. At roughly the same time, Gottfried Wilhelm Leibniz independently developed calculus. Leibniz created notation that became widely used and remains familiar today. The dispute over who discovered calculus first became one of history's most famous scientific disagreements. Despite the controversy, both men changed mathematics forever. Newton created powerful ideas. Leibniz created a practical system for expressing them. Modern calculus carries the influence of both. The impact of calculus cannot be measured only in mathematics. It became the foundation for modern engineering, physics, astronomy, economics, computing, and technology. Every aircraft design, every space mission, every advanced machine depends upon mathematics built from these ideas. Newton had discovered that mathematics was more than a human invention. It was a way of communicating with nature. Numbers revealed patterns. Equations revealed relationships. Mathematics allowed humanity to ask questions and receive answers from the universe itself. The genius of Newton was not simply that he calculated. It was that he realized reality itself could be understood through calculation. He looked at the universe and saw not chaos. He saw structure. And he gave humanity the tools to uncover it. Part 5, Principia, the book that changed human understanding forever. In the history of human knowledge, there are only a few books that completely transform the way people see reality. Isaac Newton's Philosophiae Naturalis Principia Mathematica, published in 1687, was one of those books. Known simply as Principia, it was not just a scientific publication. It was a new vision of the universe. Before Newton, science was filled with questions about movement. Why do objects fall? Why do planets orbit the sun? Why do comets travel through space? Many scientists had ideas, but nobody had created a complete mathematical explanation. Newton changed that. Principia began with motion. Newton introduced his 3 laws that explained how objects move. These laws created a foundation that could describe everything from a rolling ball to the movement of planets. For the first time, the same rules applied to Earth and the heavens. The greatest achievement of Principia was Newton's law of universal gravitation. Newton showed that every object with mass attracts every other object. The force that pulls an apple toward Earth is connected to the force that keeps the moon in orbit. A single idea united the entire universe. The book was incredibly difficult. Newton wrote it in a style designed for mathematicians. The arguments were precise. The calculations were complex. Few people could immediately understand its full importance. But those who did recognized that something extraordinary had happened. Principia changed the role of mathematics in science. Before Newton, mathematics was often used to describe observations. After Newton, mathematics became a tool for discovering new truths. Scientists could use equations to predict events before they happened. The impact of Principia spread throughout Europe. Astronomers used Newton's ideas to study planets and comets. Engineers applied his laws to machines. Philosophers considered the meaning of a universe governed by mathematical laws. However, Newton's masterpiece was not created in isolation. It was built upon the work of earlier thinkers. Galileo studied motion. Kepler discovered the laws describing planetary orbits. Other scientists developed mathematics and astronomy. Newton gathered these discoveries and connected them into one powerful system. Newton himself understood the importance of those who came before him. The famous image of standing on the shoulders of giants reflects the idea that great discoveries are built upon previous knowledge. Principia was more than a book about physics. It represented a turning point in human history. It showed that nature could be investigated through observation, experiment, and mathematics. It encouraged humanity to search for laws hidden beneath everyday experiences. Centuries later, scientists would continue building upon Newton's foundation. Einstein would redefine gravity. Quantum physics would reveal the strange behavior of matter. Modern technology would use Newton's principles to explore space. But the beginning of that journey was in 1687. A book, a mathematician, and a revolutionary idea. The universe follows rules, and those rules can be discovered. Newton had not simply explained motion. He had changed humanity's relationship with reality itself. Chapter 9: Newton's Influence on the Modern World, From Science to Technology. Part 1: The Newtonian Universe, How One Man Changed Civilization. Isaac Newton died in 1727, but his ideas continued traveling through history. His discoveries did not remain inside universities or scientific books. They entered the world around us. They shaped machines. They guided explorers. They transformed the way humanity understood reality. Newton had created more than theories. He had created a foundation upon which the modern world would be built. Before Newton, many people saw nature as something mysterious and unpredictable. Storms, planetary movements, falling objects, and natural events were often explained through philosophy or tradition. Newton introduced a different approach. Observe, measure, calculate, test, discover. This way of thinking became one of the greatest changes in human history. Newton's universe was often described as a giant mathematical system. Every object followed rules. Every movement had a cause. Every effect could be traced back to an action. This idea inspired generations of scientists and inventors. Engineers used Newton's laws to create new machines. They calculated forces. They studied movement. They designed structures that could withstand pressure and motion. The industrial world that emerged in the 18th and 19th centuries depended heavily on mathematical physics. Steam engines became one of the symbols of this new age. Although Newton did not invent the steam engine, his understanding of forces and motion helped create the scientific environment that allowed such technology to develop. Machines became more powerful because people understood the principles behind their operation. Newton's influence also transformed astronomy. For centuries, humans had watched the stars. After Newton, they could calculate their movements. Astronomers could predict eclipses, track comets, understand planetary orbits. The heavens became a place of measurement rather than mystery. One of the most remarkable consequences of Newton's work was the confidence it gave humanity. If the universe followed laws, then perhaps those laws could be discovered. This encouraged scientists to investigate everything: electricity, heat, chemistry, biology. The search for knowledge expanded. Newton also changed education. His ideas became central to scientific teaching around the world. Students learned his laws as fundamental principles of physics. His methods became part of the foundation of modern science. But Newton's greatest influence was not a single discovery. It was the belief that human beings could understand the universe. He showed that curiosity combined with mathematics could reveal hidden truths. Today, when a satellite orbits Earth, when a spacecraft travels toward another planet, or when engineers design complex technology, Newton's influence is still present. His equations continue to guide modern achievements. The world we live in is filled with technology Newton could never have imagined. Computers, artificial intelligence, space telescopes, robotic explorers. Yet behind many of these achievements is the same principle Newton discovered centuries ago. Nature follows patterns, and those patterns can be understood. The story of Newton was no longer only about one scientist. It became the story of humanity learning how to read the universe. Part 2: Newton's influence on space exploration and the journey beyond Earth. When Isaac Newton published his laws of motion and universal gravitation, he had no way of knowing that they would one day guide machines beyond the Earth's atmosphere. To Newton, the moon was an object to observe and calculate. To modern humanity, it became the first world beyond Earth that people would visit. The bridge between those two ideas was mathematics. Newton imagined a thought experiment that later became known as Newton's cannon. Imagine a cannon placed on top of a mountain so high that there is almost no air resistance. Fire a cannonball gently, and it falls back to Earth. Fire it faster, and it lands farther away. Increase its speed again, and it travels even farther. But eventually, if the cannonball is launched fast enough, something extraordinary happens. It keeps falling toward Earth. Yet because the Earth curves away beneath it at exactly the same rate, it never reaches the ground. Instead, it circles the planet continuously. Newton had described the principle of an orbit nearly 3 centuries before the first artificial satellite existed. When engineers designed rockets in the 20th century, they relied upon this exact principle. A spacecraft does not remain in orbit because there is no gravity. Quite the opposite. Gravity is constantly pulling it downward. Its tremendous forward speed means it is forever falling around the Earth instead of into it. Every astronaut aboard the International Space Station is in continuous free fall. That is why they appear weightless. The first successful satellite proved that Newton's equations worked beyond the laboratory. Soon afterwards came lunar missions, planetary probes, and deep space observatories. Every launch required engineers to calculate escape velocity, orbital transfers, and gravitational assists using principles that began with Newton. A tiny error in calculation could send a spacecraft thousands of kilometers off course. The remarkable precision of modern spaceflight is a tribute to the mathematical foundation Newton established. Perhaps the most elegant example is the gravity assist. Rather than carrying enormous amounts of fuel, a spacecraft can fly close to a planet and use its gravity to change speed and direction. It is like a perfectly timed dance with the solar system itself. Voyager 1 and Voyager 2 used this technique to visit multiple planets before continuing toward interstellar space. Their journeys were possible because scientists understood the gravitational relationships that Newton first described. Even today, every mission to Mars, every satellite providing GPS navigation, every weather forecast produced from orbit, and every telescope studying distant galaxies depends upon Newton's laws. Although Einstein refined our understanding of gravity under extreme conditions, Newton's equations remain extraordinarily accurate for most engineering problems. More than 300 years after they were written, they still guide spacecraft across millions, and sometimes billions, of kilometers. Newton never left England. Yet his ideas left the Earth. His imagination reached farther than any ship of his time could sail. The apple that fell in an English orchard eventually led humanity to the moon, to the outer planets, and beyond the edge of the solar system. His greatest journey was not one he took himself. It was the journey he made possible for everyone who followed. Part 3: Newton in the Digital Age, Computers, Artificial Intelligence, and the Future of Science. If Isaac Newton could step into the 21st century, almost everything around him would seem impossible. Carriages had become cars traveling faster than the wind. Letters had become instant messages crossing oceans in less than a second. Candles had given way to electric lights bright enough to turn night into day. Most astonishing of all, machines had begun to perform calculations that once occupied mathematicians for months. Yet beneath this extraordinary technology, Newton would recognize something familiar. The same laws. The same mathematics. The same universe. Every computer, from a mobile phone to the world's fastest supercomputer, performs billions of mathematical operations every second. Although computers use electronic circuits instead of ink and paper, they solve many of the same kinds of problems that fascinated Newton. They predict motion, model weather, calculate planetary orbits, simulate the behavior of atoms, analyze enormous collections of data. The tools have changed, but the language remains mathematics. One of the greatest revolutions of the modern age has been the ability to build mathematical models of reality. Scientists can now create digital versions of hurricanes, galaxies, bridges, aircraft, and even parts of the human body. These simulations allow researchers to test ideas safely before carrying them into the real world. An engineer can explore thousands of aircraft designs. An astronomer can watch a galaxy evolve over billions of years. A physicist can recreate the first moments after the birth of the universe. Such work would have been unimaginable in Newton's time. Artificial intelligence represents another step in this journey. Unlike traditional computer programs that simply follow fixed instructions, modern AI systems can recognize patterns, learn from enormous collections of information, and assist people in solving complex problems. Scientists now use AI to search for new medicines, study climate change, analyze images from distant galaxies, and discover subtle relationships hidden inside vast amounts of data. AI has become a powerful assistant in humanity's continuing search for knowledge. Yet artificial intelligence has not replaced scientific thinking. It depends upon it. Every model must be tested. Every prediction must be checked against evidence. Every conclusion must survive careful examination. These are principles Newton would have understood immediately. Observation before assumption. Evidence before certainty. In many ways, modern AI follows the same philosophy that guided Newton's work. It searches for patterns. It compares possibilities. It refines its answers when new information appears. While the methods are vastly different, the goal is remarkably similar: to understand the world more accurately than before. The greatest scientific challenges of our age are also connected to Newton's legacy. Can we explain dark matter? What is dark energy? Can gravity be united with quantum mechanics? Are we alone in the universe? These questions stretch far beyond anything Newton could have imagined, but they continue the path he helped create. Every generation inherits unanswered questions from the one before it. Perhaps Newton's most enduring gift was not a particular equation. It was a way of thinking. He taught humanity that nature is understandable. That careful observation can reveal hidden truths. That mathematics can describe the deepest workings of reality. Those ideas remain at the heart of science today. If Newton were alive now, he would almost certainly be amazed by modern technology. But after the surprise faded, he might ask the same question that had guided him throughout his life. What mystery shall we investigate next? That question still drives science. And as long as people continue asking it, Isaac Newton's influence will never truly end. Part 4: The Future Beyond Newton, Humanity's Next Great Discoveries. Isaac Newton spent his life asking questions that few people had ever considered. Why do objects fall? Why do planets move? What is light? Can mathematics describe the universe? He answered many of those questions, but he also left behind something even more valuable. He showed that every answer leads to new questions. The pursuit of knowledge has no final destination. Each generation stands on the discoveries of the last and looks a little farther into the unknown. Today, scientists are investigating mysteries that would have seemed almost magical in Newton's time. Powerful telescopes are searching for planets orbiting distant stars. Some of these worlds lie in regions where liquid water could exist, raising one of humanity's oldest questions. Are we alone in the universe? Thousands of exoplanets have already been discovered, and new observatories continue to expand that number. Every discovery reminds us that our solar system is only one small neighborhood in a galaxy containing hundreds of billions of stars. Another mystery lies much closer to home, yet remains invisible. Astronomers have found that galaxies rotate too quickly for the visible matter they contain. Something unseen appears to provide additional gravity. Scientists call this dark matter. No one has yet directly detected it, but its gravitational influence seems to shape galaxies throughout the cosmos. Even stranger is dark energy. In the late 20th century, astronomers discovered that the expansion of the universe is accelerating. Instead of slowing down under gravity, the cosmos appears to be stretching faster and faster. Whatever causes this acceleration remains one of the greatest unsolved problems in physics. Together, dark matter and dark energy may account for most of the universe, leaving ordinary matter, the stars, planets, and people we know, as only a small fraction of all that exists. Physicists also seek a deeper goal. Newton explained gravity. Einstein redefined it as the curvature of space-time. Quantum mechanics revealed the strange behavior of particles. But these great theories do not yet fit together perfectly. Some researchers search for a theory of everything, a single framework capable of describing all the fundamental forces of nature. Whether such a theory exists remains unknown, but the search continues with the same spirit of curiosity that guided Newton. Technology is becoming one of humanity's greatest scientific partners. Robotic explorers travel where people cannot. Artificial intelligence helps researchers analyze enormous amounts of information. Quantum computers promise entirely new ways of solving certain problems. Future generations may possess tools that seem just as astonishing to us as modern computers would have seemed to Newton. As humanity looks outward, space exploration is entering a new era. Plans for long-term lunar bases, human missions to Mars, and increasingly capable robotic probes suggest that the coming centuries may transform our place in the solar system. One day, future explorers may walk across distant worlds carrying instruments built upon principles that began with Newton's work. His influence will travel wherever humanity goes. Yet perhaps the greatest frontier is not a place. It is understanding itself. Every discovery changes how we think about reality. Every experiment challenges old assumptions. Every generation rewrites a small part of humanity's story. Science is not a collection of finished answers. It is an ongoing conversation between curiosity and evidence. If Newton could see the world today, he would almost certainly be astonished. But after recovering from that astonishment, he would recognize something familiar. Scientists still observe carefully. They still test ideas. They still argue, revise, and improve their understanding. The method has endured because it works. The apple that inspired a question about gravity did more than explain why objects fall. It began a chain of discovery that continues across centuries. From observatories on mountaintops to spacecraft between the stars, from laboratories studying quantum particles to computers searching for hidden patterns, Newton's legacy remains alive. The future will bring discoveries that none of us can predict. But if history teaches us anything, it is this. The next great revolution in science may begin with a simple question asked by someone curious enough to wonder why. Chapter 9, Part 5 concludes Newton's legacy. Newton's influence cannot be measured only by the discoveries he made during his own lifetime. It can also be measured by the discoveries that became possible because of him. Every scientific generation has inherited something from Isaac Newton. Some inherited equations. Some inherited methods. Others inherited something less tangible but even more valuable: the confidence that the universe can be understood. When Newton published Principia, he could not have imagined the technologies that would one day emerge. He could not have imagined aircraft crossing oceans in hours. He could not have imagined satellites orbiting the Earth, allowing people to communicate instantly across continents. He could not have imagined robotic spacecraft photographing distant planets or telescopes observing galaxies billions of light years away. Yet each of these achievements rests upon principles he helped establish. Modern civilization depends upon precise understanding of motion and force. Bridges remain standing because engineers calculate stresses using the laws of mechanics. Aircraft fly because designers understand forces acting upon wings. Cars protect passengers through careful application of physics. Even the tiny sensors inside smartphones rely upon principles connected to Newtonian mechanics. His work quietly surrounds us every day. Perhaps the greatest tribute to Newton is that many people use his discoveries without realizing it. When a satellite guides a driver using GPS, when weather forecasts predict the path of a storm, or when a spacecraft reaches another planet, Newton's ideas are working silently in the background. His science has become part of everyday life. Yet science did not stop with Newton. It never stops. Einstein expanded our understanding of gravity. Quantum mechanics revealed a microscopic world stranger than anyone had imagined. Artificial intelligence now assists researchers in analyzing information on a scale impossible for any individual. Each breakthrough builds upon those before it. Knowledge is not a series of isolated discoveries. It is a continuous chain stretching across centuries. Newton himself understood this better than most. His famous reflection about standing on the shoulders of giants reminds us that progress is rarely the work of one person alone. Every scientist inherits the work of previous generations and leaves something for those yet to come. Newton was both a student of history and a creator of history. Today, humanity faces questions that remain unanswered. What is dark matter? What causes dark energy? Can gravity and quantum mechanics be united? Is intelligent life waiting somewhere beyond our solar system? The answers are still unknown. But the method for searching began long ago, with careful observation, logical reasoning, mathematics, and experiment. The true legacy of Isaac Newton is therefore much larger than gravity or calculus. He transformed curiosity into a disciplined search for truth. He demonstrated that nature follows discoverable laws. He encouraged humanity to replace assumption with evidence. That way of thinking continues to shape science, technology, and civilization itself. As the 21st century unfolds, humanity prepares for journeys Newton could scarcely have imagined. Permanent bases on the Moon. Human explorers on Mars. Artificial intelligence working alongside scientists. Powerful telescopes searching for signs of life around distant stars. These are not departures from Newton's legacy. They are its continuation. The story of Isaac Newton is, in many ways, the story of human curiosity. One person asked why an apple falls. Generations later, humanity reaches for the stars. And the journey is far from over. Chapter 10, Newton Awakens, a Genius Confronts the 21st Century. Part 1, The Man Who Returned to the Future. For more than 300 years, Isaac Newton rested in history as one of humanity's greatest thinkers. His name was written in textbooks. His discoveries were taught in classrooms. His equations guided machines that traveled beyond Earth. But what would happen if the man himself could return? What would Isaac Newton think of the world his ideas helped create? Imagine Newton opening his eyes in a century he could never have predicted. The familiar streets of 17th century England are gone. The sounds are different. The lights are brighter. The world moves faster. Machines travel without horses. Voices travel instantly across oceans. People carry small devices more powerful than the largest calculating machines of his own time. At first, Newton would search for explanations. He would observe. He would question. He would investigate. The same curiosity that drove him as a young scholar would immediately awaken. For Newton, the unknown was never something to fear. It was something to explore. He would look upward and see something impossible. The night sky would no longer belong only to nature. Among the stars would be artificial objects created by humans. Satellites. Machines orbiting Earth. Newton would understand immediately that they were following the laws he discovered. The invisible force he had studied now guided human creations around the planet. He would learn that humans had traveled beyond Earth. Astonishment would become admiration. The Moon, which he had studied through mathematics, had become a place where people walked. Rovers moved across Mars. Spacecraft traveled beyond the outer planets. The solar system had become a destination rather than a distant mystery. But perhaps the greatest surprise would not be space. It would be the machines that helped humanity think. Computers. Artificial intelligence. Systems capable of analyzing information, recognizing patterns, and assisting in discoveries. Newton would see that mathematics had grown into a force that shaped the entire civilization. He would recognize something familiar. The machines were not magic. They were built from principles. They followed rules. They relied upon mathematics. The universe was still speaking the language Newton had spent his life learning. But he would also discover that science had moved beyond his own understanding. Einstein had shown that space and time were connected. Quantum physics had revealed that nature behaved differently at the smallest scales. The universe was not the simple clockwork machine many had imagined. It was deeper and stranger. Newton might feel humbled. But he would not feel defeated. Humility was part of true discovery. Every answer created new questions. Every discovery opened another door. Standing in this future world, Newton would finally see the full impact of his life's work. He had not simply explained gravity. He had helped create a way for humanity to explore everything. The boy who once built mechanical models in isolation. The young scholar who questioned the movement of objects. The scientist who looked at light, motion, and the heavens. Had become part of a story far larger than himself. And as Newton looked upon the modern world, he would ask the same question he had asked throughout his life. What remains to be discovered? Part 2: Newton encounters space, technology, and the machines of the future. Isaac Newton had spent his entire life studying the forces that shaped the universe. But nothing could have prepared him for the scale of human achievement in the modern age. The world he entered was not a world of wooden ships and candlelight. It was a world where humans had learned to fly. A world where machines traveled beyond Earth. A world where invisible signals connected billions of minds. Newton's first encounter with modern technology would likely begin with a simple question. How does it work? That question had guided him throughout his life. He would not simply admire the inventions. He would take them apart in his mind. He would search for the principles behind them. A modern aircraft would fascinate him. He would see a machine heavier than any bird carrying hundreds of people through the air. But Newton would recognize the forces involved. Lift, thrust, gravity, motion. His laws were still present. The aircraft was not defying nature. It was cooperating with nature. Then he would see spacecraft. Machines designed not merely to travel across Earth, but to leave it. Newton would understand that these journeys depended on the same gravitational relationships he had discovered centuries earlier. A rocket escaping Earth. A satellite orbiting the planet. A spacecraft traveling toward another world. All were movements written in the mathematical language he helped create. Perhaps the most emotional moment would come when Newton looked at images of Earth from space. A blue planet floating in darkness. No borders visible. No divisions. Just one world surrounded by an enormous universe. The same Earth whose gravity he had studied was now seen from beyond its atmosphere. Then came computers. To Newton, calculation had always been a powerful tool. But modern computers would appear almost unimaginable. Machines capable of performing billions of calculations in seconds. Systems that could store more knowledge than entire libraries. Devices small enough to fit into a person's hand. Yet Newton would quickly understand the foundation. A computer was not thinking like a human. It was following rules. It was processing information. It was using mathematics. The machine was another expression of the same principle that had guided his work. The universe can be described through patterns. Then humanity would show him artificial intelligence. A new kind of technology. Machines capable of learning from information. Systems that could recognize images, understand language, and assist with scientific discovery. Newton would see both the possibilities and the questions. Would these machines help humanity discover new truths? Could they reveal patterns hidden from human minds? Could they help solve mysteries that had challenged scientists for centuries? The possibilities would excite him. But Newton would also ask deeper questions. What is intelligence? What separates calculation from understanding? Can a machine discover, or does it only imitate discovery? These questions would remind him of the mysteries he had explored throughout his life. The future would not replace Newton's ideas. It would demonstrate their power. The technology surrounding him would be built upon centuries of scientific progress. Every satellite, every computer, every spacecraft, every mathematical model was part of a journey that began with people asking questions about nature. Newton had once looked at the universe and seen hidden laws. Now he would look at humanity and see something equally remarkable. A species that had learned to use those laws to transform its world. The greatest invention was not the rocket, not the computer, not artificial intelligence. It was the human desire to understand. The same curiosity that drove Newton still burned within humanity. And that curiosity was now reaching further than ever before. Part 3, Newton discovers the universe beyond his imagination. For most of Isaac Newton's life, the universe was something observed from the surface of Earth. He studied the moon through a telescope. He calculated the movements of planets through mathematics. He looked toward the stars and wondered about the laws that governed them. But now, standing in the modern age, Newton would discover that humanity had traveled far beyond simply observing the cosmos. Humanity had entered it. Newton would first be shown images from modern telescopes. They would not resemble the simple points of light visible from 17th century England. Instead, he would see enormous clouds of gas where stars were born. Galaxies containing billions of suns. Black holes where gravity became so powerful that even light could not escape. The universe had become larger and stranger than anyone of his time had imagined. The discovery of galaxies beyond the Milky Way would be one of the greatest surprises. In Newton's era, many believed the stars existed within a relatively small cosmic structure. Modern astronomy revealed something astonishing. The Milky Way is only one galaxy among countless others. The observable universe contains hundreds of billions of galaxies, each filled with stars, planets, and possibilities. Newton would understand the importance immediately. He had always believed nature contained hidden truths waiting to be discovered. The size of the universe had simply expanded beyond what his generation could measure. The unknown had grown. But so had humanity's ability to explore it. Then scientists would explain Einstein's discoveries. Newton would learn that his description of gravity had been revolutionary but incomplete. Gravity was not simply a force pulling objects together. According to Einstein's theory of relativity, massive objects bend the fabric of space and time itself. Planets orbit because they follow the curves created by these cosmic structures. Newton might find this strange at first. But he would recognize the beauty of the idea. Einstein had done something similar to what Newton himself had done. He had looked at ordinary observations and discovered a deeper reality hidden beneath them. Then came quantum physics. This would challenge Newton even more. The tiny world of atoms and particles behaved in ways that seemed almost impossible. Particles could exist in uncertain states. Objects could behave like both particles and waves. The foundations of reality appeared far stranger than human intuition suggested. Yet Newton would notice something familiar. The scientists of the quantum age were still searching for patterns. Still creating mathematics. Still testing ideas. The methods had remained the same, even though the universe had revealed new mysteries. Perhaps the most astonishing discovery would be the possibility of planets around other stars. Newton had studied the solar system. Modern humanity had discovered thousands of worlds beyond it. Some were giant planets larger than Jupiter. Others were rocky worlds that might contain the conditions necessary for life. Newton would look at these distant planets and realize something profound. The universe was not built around humanity. Earth was not the center. The cosmos was vast beyond imagination. Yet within that vastness, a small species on one small planet had learned to understand it. He would see spacecraft carrying instruments across the solar system. Machines exploring planets, moons, asteroids, and comets. He would watch humanity sending messages toward the stars. Not because humans had conquered space, but because they were curious. That curiosity would be the thing Newton recognized most. Technology had changed. Knowledge had expanded. The universe had grown larger. But the human desire to understand remained exactly the same. The man who once studied a falling apple now stood beneath a universe billions of times larger than he imagined. And instead of feeling overwhelmed, Newton would smile. Because the greatest discovery was not that humanity had found all the answers. It was that there were still endless questions waiting. Part 4: Newton and the Age of Artificial Intelligence, the New Mind of Humanity. Isaac Newton had spent his life trying to understand the relationship between thought and reality. He believed the universe followed patterns. He believed mathematics revealed those patterns. He believed that careful reasoning allowed the human mind to uncover truths hidden within nature. Now, in the modern age, Newton would encounter something entirely new. A creation of humanity's own intelligence. A machine that could process knowledge. A machine that could learn. Artificial intelligence. At first, Newton would approach AI like any other mystery. He would not accept it simply because people claimed it was remarkable. He would ask questions. How does it work? What principles allow it to learn? What limits does it have? What does it truly understand? Scientists would explain that modern AI systems are built using mathematics, algorithms, and enormous amounts of information. They do not think exactly as humans do. Instead, they find patterns. They analyze relationships. They make predictions based on what they have learned. Newton would recognize something familiar. The foundation was mathematics. Behind the complex machines were numbers, equations, and logical structures. Just as he had used mathematics to describe the movement of planets, modern scientists used mathematics to create systems capable of analyzing the world. He would be fascinated by how AI could assist science. Machines could examine enormous amounts of astronomical data. They could help discover new materials. They could search through millions of possible chemical structures. They could help scientists understand diseases and develop new treatments. But Newton would also see the deeper questions. Throughout his life, he had explored the relationship between knowledge and understanding. Now humanity had created machines that could produce answers. But could they truly comprehend the meaning behind those answers? This question would remind Newton of his own discoveries. Knowing how gravity worked was different from understanding why the universe existed. Calculating motion was different from understanding the purpose behind existence. Science could reveal mechanisms. But deeper questions remained. Artificial intelligence represented a new stage in humanity's intellectual journey. For thousands of years, humans had created tools to extend their abilities. The telescope extended sight. The microscope extended observation. The computer extended calculation. AI extended the ability to analyze information. Newton would see that every great invention had followed the same pattern. Human curiosity created tools. Those tools revealed new possibilities. New possibilities created new questions. The cycle continued. Perhaps he would be most amazed by one simple fact. Humanity had created machines that could help humanity discover more about itself. The same species that once wondered about falling objects had now created technology capable of exploring the deepest questions of nature. Yet Newton would offer a warning. Knowledge alone was not enough. Wisdom mattered. The power to discover must be balanced with the responsibility to use discoveries wisely. Science could improve the world, but only if guided by thoughtful decisions. Looking at artificial intelligence, Newton would see both a tool and a challenge. A tool for discovery. A challenge to understand what intelligence truly means. And perhaps he would ask one final question. If the human mind can create something capable of learning, what does that reveal about the universe that created the human mind? The mystery that had fascinated Newton throughout his life remained. The universe was still full of wonder. Humanity had not reached the end of discovery. It had only reached another beginning. Part 5, The Final Reflection, Newton's Message to the Future. Isaac Newton spent his life searching for answers. He searched in mathematics. He searched through experiments. He searched among the stars. But perhaps his greatest discovery was not a law or an equation. It was a way of looking at the world. A belief that curiosity, patience, and reason could reveal the hidden structure of reality. Standing in the modern age, Newton would see a world beyond his imagination. He would see machines traveling beyond Earth. He would see humanity exploring the depths of space. He would see computers performing calculations that would have taken generations in his own time. He would see artificial intelligence helping scientists uncover new patterns in nature. But among all these wonders, Newton would recognize something unchanged. the human desire to understand. The same curiosity that led him to study falling objects now led humanity to study galaxies. The same questions that guided his experiments now guided missions across the solar system. The search continued. Newton might look back at his younger self. A child building mechanical devices. A student questioning accepted ideas. A scientist working alone through long nights. He would see that every moment of curiosity had been part of a much larger journey. His life had shown that great discoveries do not begin with certainty. They begin with questions. Why? How? What if? These simple questions have carried humanity from observing the heavens to exploring them. Newton would also understand something important. Science is never finished. A discovery does not close the door. It opens another. Gravity led to relativity. The study of light led to quantum physics. Mathematics led to computers and artificial intelligence. Each answer created a new mystery. Perhaps Newton's final message to the future would not be about gravity or mathematics. It would be about curiosity. Do not stop asking questions. Do not accept that the universe is fully understood. Do not believe that today's knowledge is the final truth. The universe remains vast. There are stars we have never visited. Worlds we have never seen. Questions we have not yet imagined. And somewhere in the future, another person may ask a simple question that changes everything. The story of Isaac Newton is not only the story of one extraordinary man. It is the story of humanity's greatest ability. The ability to wonder. A falling apple became a question. A question became a theory. A theory became a revolution. A revolution became a future where humanity reached beyond Earth and into the unknown. Newton once looked at the universe and discovered that it was governed by hidden laws. Centuries later, humanity continues that search. The journey that began with one curious mind is still unfolding. And the greatest discoveries may still be waiting. The end. Isaac Newton, the man who revealed the universe. If you like these kinds of audiobooks, feel free to like and subscribe to the Sleepy Universe. It really does help to grow the channel, and it lets YouTube find you from one sleepy mind to another. Sleep tight. Good night.